Что-что? А что с ним стало? Ну, вроде бы там контроль на месте, все на месте.
Нет, просто ему могла остаться иллюзия, что я ему обещал быть председателем.
Ну,
Не
слушай,
знаю.
может быть, можно без председателя начать. Да. Ну, хорошо. Я думаю, нормально, а что? Уже народ уже выучил, ты такой. А что с Антоном, все нормально? А, понял. А. Самый председатель. Привет. Чего? Ну, как-то все так выдержали. Выдержали проверку банкетом. Как не остановить? Давай.
Раз.
Да нет, я там сейчас начну. All right, I think congratulations on everybody passing the banquet test. The first lecture after the banquet.
Well, it's know that maybe young people don't remember, but that was always the most respectable position at any conference. The first speaker after the conference dinner.
Yeah.
So, of course, Professor Apnikov.
Thank you. So I'll start with maybe explain. So some remark about the previous lecture is that I may have slightly oversimplified the life. So if we have this G covariant cohomology of subspace X, maybe call it AI. These are in real life. In real life, they are not given as cohomology of some complex. Like, for instance, we talked about K groups, and we divide them individually, not as cohomology of some complex. But still, they fit in this pattern, which we have a cone of a map. So I have cohomology, so if I have X going to Y, going to so maybe a map F, there's a cone of F. So this is what should happen is that after the H cohomology of Y maps by pullback to the H cohomology, maybe ith cohomology of X, and there's a map again by pullback to the ith cohomology of the cone. And there is a map which shifts cohomological grading by one. So they fit in this long exact sequence. If I have a cone of complexes, then the cohomology form a long exact sequence. That's what we were using, not the fact that we had when we did the computations. We used the fact that this fit in a long exact sequence, and that's so. It's a general remark. Now go back to our order of the business is to compute. So maybe I remind you what was where the end of the lecture found us last time is that we had some a unitary group of some vector space V is naturally acting on the projectivization of that space V, and we would like to know what is the U-equivalent K-theory of that projective space. This is complex vector space. And what we did is we took this vector space, maybe call it again. Now this is our space V. We can think of the projective space as I take the sphere here, maybe I'll just write S, and I have to mod it by U1, or maybe S. This is sphere dimension, well, if this is of dimension N, this is a sphere of dimension 2n minus 1. And this quotient is the projective space. And this fits in this exact sequence when we have the sphere, we have the disks that fill it, and we have the corresponding, so there's a disk. And when we take the disk and collapse the sphere, that we get the top space. So it's an example of that. Right? That makes sense? And now, what's the relation? What's the relation of this cohomology of the projective space? Well, if I have, as we discussed last time, if I have a free quotient by a group, so if I have, in general, if I have G equivalent theory of some space X, and if G acts freely, X has free action, then to give a vector bundle on X is the same as to give a vector bundle on, just really take the quotient. And so maybe I'll skip one. If I apologize if this complicates the video process. So if I want to know U-equivalent cohomology of the projective space, that is the same as UV cross U1, where this U1 is the center of this group. So they together act of that sphere. By this principle. That's clear. Generalizing this principle, so generalizing the principle, suppose the action is not exactly free, but suppose I ask myself, what is the G equivalent K theory of a homogeneous space? What does it mean to give a equivalent bundle on a homogeneous space? Like imagine I have like an actual three-dimensional sphere, and I want a bundle which is equivalent under all rotations. Then it's enough, so maybe I'll have to draw it a little smaller. Where's the eraser? Let me try a little smaller. So suppose I want a vector bundle on a sphere which is equivalent with respect to all rotations. Then I look one point. One point is fixed by rotations here. So I have to tell you how this stabilizer of a point, how its action lifts to the action on the fiber. Right? So if I tell you how the stabilizer of a point acts on the fiber, then there's a unique way to extend to the action on the group on the whole homogeneous space. That clear? So this means that this is the same as just the action of the group on the fiber, that is to say, the H equivalent homology of a point. Right? Which is concretely, what is it? This is representation. This is the ring of representations of the group. So you can think of this as kind of integer valued functions of an element H considered has to be mod conjugation. And what does it mean? So what does it mean, the integer valued function invariant under conjugation? It means integer linear combinations of characters of reducible representations. So this is Z, means Z linear combinations of the characters of irreps. And so for instance, if the group is a circle, then this is just like a Laurent polynomial with integer coefficients. So now with this, we want to write the long exact sequence for this inclusion. So we have so let's for simplicity, let's denote this whole group G. Then we're going K naught G of the sphere. There is a map by restriction to K naught of G of the disk. There's, by definition, there's a map from K naught G of the corresponding Thom space. So when you take the disk and you collapse the sphere. And in principle, there are connecting maps. We'll discuss the connecting maps in a second. So in principle, there's some kind of connecting maps here. But what is this? What's written here? Here we have so what's written here? Here, this disk, that's contractible. So this is just the action there is the same as action on the point, on the center of the space. So this is just the representation ring of the group G. Right? And this is a homogeneous space. A sphere, the group acts transitively, so that's a representation ring of the subgroup, which the subgroup is the stabilizer. So if I have a point, so I have some point P, I have a group acting, this maybe G, maybe I'll write G, stabilizer of a vector, of a non-zero vector, GV. So I have some point, and there's a stabilizer of that, so the GP, the stabilizer. This is H. Now, and what's this? Yeah. Term of the inclusion. So this is inclusion of the. So this is a trivial vector bundle over a point. So we take this vector bundle, we contract infinity to one point. Right? So this is the Thom space for the. So this okay, all right. Thank you. This is the Thom space for the inclusion of 0 into the total space of V. So we take the V, we contract to the point. So what is this? This is the interesting part. These are What's by definition here? These are representations of G that are trivial when restricted to the group GD, which is. So what's the group GD? The group GD, it's the group where I have to fix some vector. So maybe I have some matrix with some eigenvalue, maybe A1 or maybe, and then some matrix G prime, and then I have a variable T, and this satisfies the condition that A1 times T equals 1. Right? So when they both together act together, so they have together fix a vector. So one can scale a vector. So this has to be a vector which is eigenvector with respect to this. With the eigenvalue with this has to do with it. Right? That makes sense? Right, so what fixes a vector under this action? It has to be an eigenvector for the matrix here, and this has to be more the eigenvalue. Or the inverse of the eigenvalue. That everybody agrees with that? So these are functions on the group G. So I'll just write I'll write R. These are functions on the group G modulo conjugation. And these are functions that vanish when I restrict to the subgroup. Okay. Which functions on the group G vanish when I restrict to the subgroup? Well, that's just what is the locus of those matrices that have an eigenvector? That's the study in linear algebra. So this is naturally identified by what? To have an eigenvector, it's a codimension one condition, and given by, so this I'll write it like that. So what's that? This is all possible function times the equation of having an eigenvector, means the determinant of 1 minus Tg. If this determinant vanishes, then this matrix has an eigenvector, and this is the inclusion. That makes sense? So, and now to continue with the long exact sequence, we see from this that this map is an inclusion. That's injective. Therefore, there's no connecting map here. This thing is 0 because that's K-theory of a point. So this is an inclusion here. So there's no map coming this way. This is 0 because it's K-theory of a point, and so therefore this is also 0. So the K-aught is 0 in this sequence. So in principle, there's a connecting map. We don't know, but since this is injective, the map from here is 0, and this is 0, so this is 0, and similarly the other way. So K-aught of a point is 0. Aught homology of a point is 0. Right? Group element. So G is in UV, and T is in U1. It's this element, G. What? G is an element in my group. So it's elements in K-theory, their K-theory of a point are functions on the group. So you can evaluate a function. It's natural to give a you want an element in K theory, you give a conjugation invariant function of an element of the group.
You say what, but sounds like O. K-O, whatever.
It means knockout, right? KO, is that? Yeah, well, look, okay. So this is to finish. So what do we have learned? We have learned that if I take U of V equivalent homology of projective space, this is equal. You take K U of V of point. I join one element with the relation T plus minus, and this becomes this guy. This would be the line bundle O of 1 on this projective space. And the relation is that the determinant modular condition, determinant of 1 minus Tg is 0. That's clear? G is an element, so this is what? These are functions. This ring, these are functions of an element G. If you have a coordinate here, and here's the coordinate G. So the elements in K theory, they're functions on a group. So if you wanna write an element in K theory, you just write a function of a group. So this we've written function on product of two groups. Yeah, it's right. Modular conjugation. Okay? And this you can do, when you do this Thom computation, you can do it in stages. And so if I compute the Thom space, you can add Thom space to Thom space. And that has, you can do it. Here we had, so this says that if I don't consider the whole group U of V, but take a subgroup of the form inside here, if I have V decomposed into V1, V2 plus something. So I can a subgroup which is the product of smaller unitary groups. Then I can do the same computation in stages, and I get the same answer. But it's just the conjugation will be with respect to a smaller group. That clear? The answer is just the same. So in particular, if I'm interested in torus equivalent K theory, so in particular, an example of that is I have just the diagonal matrices, product of U1s. So this would be if I'm interested in torus equivalent homology of projective space. But it's the same thing. It's the functions on a torus. So I'll write in Laurent polynomial as A1 plus minus, A2 plus minus, and so forth. These are Laurent polynomials on this torus T. And then I joined one more variable T. And I consider the equation that the product. So this equation then becomes the product of 1 minus T times AI equals 0. That clear? That's the same. So if you want the algebraic, you have an algebraic GL and topological, the corresponding compact, that's the same. Because for many reasons, like topologically, the reductive group contracts to the compact group and so on and so forth. So that's okay. So now let's go back to this, revisit this computation from the point of view of what we were doing last time. Last time I drew this Kazul complex. So what is this? This is what I'm trying to say, that this concrete representative of this relation, or maybe the concrete representative of the relation better, more factorially if I write, I found it, if I write T inverse G inverse, of course the same equation. This guy here, this equation, that is the Kazul complex. These are polynomials in. This is supposed to be a function on a product of a group and one more scalar, and invariant under conjugation in the group. And the condition is that the scalar is basically it says that this scalar is an eigenvalue of an element in the group. That's a polynomial with integer coefficients, this. Or equivalently is this. But this is a little better because it's actual representative of the Kazul complex. And why is this? Because right, we'll do the resolution. So we'll just compare with this in a second. So what was the so this is I it's always good to take a break in the lecture and draw the table of all monomials, which I always never miss an opportunity to do this. So the table of all monomials is x1, x1 square, x2, x2 square, x1, x2, and so forth. Maybe x1, x2 square. And so, what? Yeah, there are many pictures that we'll keep for the next lecture, yeah. So this is what you're trying to say. We're trying to take this function 1 as a module over all polynomials. That's the skyscraper. That's the it's kind of like the delta function at 0. It's the skyscraper sheaf at the origin. It's something on which this is by definition this whole I don't know, right, Z. Since we're doing integer coefficients, let's do Z. This is mod, or no, we're doing sorry, I forgot. We're doing complex vector bundles. Got carried away. Sometimes I get carried away in the lectures, I apologize. So this is complex. So this is polynomials modulo the ideal, which the ideal is the ideal generated by x1, x2. So this is the red, in red is the ideal. If we wanted to write a resolution of this structure sheaf, well, how we go? We start with this structure sheaf. By definition, that maps x1, x2, which is what? These are functions. This is polynomial functions. Functions on V, right? And then the kernel of that is generated by x1 times functions plus x2 times the functions. And then and so this would be I take this picture and I subtract what's generated by x1 and also subtract what's generated by x2. But then I subtracted what's generated by x1 and x2 twice, so I have to put it back. So I take this guy and I have to put it back. So this would be x1, x2 times cx1. And this would be exact. So this is, if you compute the character of what we're doing here, this would be, this is what's written here. So this is, if I look at this as elements, if you pick this I consider these guys as elements. So I view the terms in this complex, I view as elements well, in this case, K, well, say U2 cross U1 equivalent to homology of the vector space. So what's it going to be? Here sits nothing. It corresponds to trivial representation. Okay? This says 1. So here I have to subtract, and I subtract what? This x1 and x2 are a basis. X1 and x2 are a basis in linear functions. Right? So linear functions is V is a representation. Linear functions of V form a dual representation. So I subtract. So I have. Sorry, I apologize. I can't write formulas from the side. Resolutions from this side is fine, but formulas from this side is bad. So I'll write 1 minus. So I have functions dual representation, and in particular, how is the center is supposed to act? The center acts by scaling on the space. On the dual representation, it will act by inverse scaling. So this would be T inverse. And then what's written here is the wedge. So this will be plus wedge 2 of the dual representation times T minus 2. So if I compute the character of the space, so this is, if I compute the character of the space, I get what? I get, so if I compute how an element G acts in this representation, well, it's going to be 1 minus, so it will be the trace, in the dual representation, trace of G inverse, times T minus 1, plus this will be the determinant of G times T inverse. This whole thing is the determinant of 1 minus T inverse G inverse. Okay. So this element here, this particular polynomial, this slightly better polynomial, that actually represents a very specific element, very specific generator in here, namely this Kazul complex. G inverse, yeah, a determinant of G inverse, because dual representation is right. There's a unity of math, yes. Yeah, but it's so maybe Vanya is making a good point. There's this kind of there's a funny relationship between topological and algebraic key theory, and sometimes they very closely related, sometimes they diverge, but they're certainly very, very closely related for a point. So any representation of a compact group is holomorphic. So this is and so any spaces that are built for points in some very simple ways, they inherit spaces that build from points and representation in some kind of ways. They inherit the fact that the topological and algebraic key theory remain closely related. In fact, sometimes the same. Yeah. Sure.
So then it will be uniformity formula, algebraic. What about topological part of this? For arbitrary V, which is for young.
This is for any V. For any V whatsoever, yeah. So if for any representation, that's still the same. So it's just if what does it mean have representation? Representation have some subgroup in here. Right? So here's with respect to all things, and representation means I choose a subgroup in here. Yes, please. Where? Here? There? But it's just if you think what is these are functions on a group that have to become 0 when restricted to a certain locus. And what's the locus? The locus is locus of matrices that have an eigenvector given with this eigenvalue. Right? Well, because this vector, so this is, what is this, what's the sphere? The sphere is a homogeneous space. And what is fixed as a point? The fixed as a point, I have to first have to be, this point first have to be an eigenvector with respect to this group. And second, its eigenvalue has to be this, or inverse to this.
So there's another choice, like quotient side, A1 is 1. Is that also another choice?
Say it again?
So is there any other choice of that condition, like A1 divided by 2?
Well, I don't know. Maybe we can talk a little more. I think they're all equivalent. But so this is, of course, as an equation of the group. This defines this. If t, since t and g in invertible, this equation defines the same locus. However, this is a particularly, you can say, this is a particular nice section of the corresponding line bond. Right? Okay.
Still, for arbitrary representation, Gauss resolution will be exactly two-bit more complicated. And then the right side algebraic will be different.
I think, Banya, I think what you're saying is that of course you can take some number of copies. So what you can so you could be Trudy. What you're talking about is this. So if I have a tensor u v1 product u v2 embeds into u of v1 tensor v2. Right? You agree? And so if you take this subgroup, you're going to get your Jacobi-Trudy form. So this is the Kazul resolution is completely canonical, is invariant under all possible groups. In particular, if you have any representation of any group, the Kazul resolution will be Kazul resolution. That good? So so I have to look at my notes. Where was I supposed to say next? There's so many things to say, but maybe. I'm not sure what's the best way to proceed. Maybe I'll say a few words since this course is supposed to get to elliptic homology at some point, right? So maybe it's a good way to say what is the analog of, while we have this formula on the board, what would be the analog of elliptic homology analog of this formula? So and we can before we talk about general group, let's fix some so let G be a compact group. E.g., G could be U1. Let's start with U1. I think in topology, in some sense, everything else. So in representation theory, there's many interesting groups, but in topology, in some sense, this is the most interesting. So this is then we the U1 occurring K theory of a point. This is the representation ring of the group U1. That's the same as integer valued polynomial, integer coefficients maybe in some variable t, just like we discussed it last time. And this is, you can think of this as well, these are trigonometric polynomials on the group itself. We have this, we had all this, so elements in K theory of a group, you should really think of functions on the group. And what they are, if you think of a group as S1 or R mod Z. In this realization, these are trigonometric polynomials with integer coefficients. So Make sense? And so, right, or also around polynomials on C times. That is to say, this is what? Dot C times. C times is the complexification of my group. So then you would like to say kind of elliptic U1 or point. Well, you would like it to be elliptic functions or some functions on elliptic functions on your group U1. And so this is we'll get to that in a second. So, or that is to say functions, i.e. functions, these are holomorphic functions here. So these are functions holomorphic functions on C times we take mod powers of Q. A holomorphic function invariant with respect to Q. Now anybody says there's none such. There's no such functions. There's no non-constant function. And that's actually can be important when you think about. So one important property of Kirchhoff genus, key property proven by Kirchhoff, is rigidity. And in the end, it reduces the fact there's no holomorphic functions on this elliptic curve. But that's not really an obstacle, because remember when we talk about, well, I don't know, maybe whether you remember or not, I'm going to remind you, is that these equivariant cohomology groups of X, they should take values, they can in principle take values in vector spaces and so forth, but they have to take values in some category where exact sequences make sense. So instead of saying these are more, so instead of saying that these are, so what does it mean to say equivariant K-theory? So every equivariant K-theory group is a module over equivariant K-theory of a point. So everything is a module over this ring. But it might as well be a sheaf of modules over some global objects. So they may very well take values in sheaves. Well, in this case, coherent sheaves. Sheaves of over something. Could choose on something. So in particular in this case, they might be for elliptic homology. So H, whatever it is, elliptic, whatever it is, may very well be, this could be a sheaf. This really could mean a sheaf on H G elliptic point, or just write, maybe I'll write elliptic. G for U1, for G equals U1, this is a sheaf on elliptic curve. In other words, say it one more time. K-theory, equivalent K-theory is a module over a ring, namely the equivalent K-theory of a point. Module over ring is a special case of a sheaf on an algebraic variety. It's just your algebraic variety is affine, and the sheaf is given. Well, it's just a module over a ring. But if algebraic variety is not affine, like the elliptic curve, makes total sense to say this cohomology should go to a sheaf somewhere. It doesn't have to be a vector. So cohomology doesn't have to be a vector space. Can be a bundle over some other space or a sheaf on some other space. It's kind of an important point. In other words, the values here, it's okay for this to take values not in vector spaces, not in modules over some ring, but in vector bundles over something else, or somehow sheaves over something else, in particular sheaves over the elliptic curve. That makes sense? Well, a meromorphic elliptic function, that's easy. It's a meromorphic function here. So it's easy to say what's a meromorphic. We don't want to be, here we don't take rational functions, we take polynomials. But we could have taken rational functions. And then the analog would take meromorphic functions here. And that would be just meromorphic functions on this elliptic curve.
Okay, but it was a good point.
What?
Quite a big question, right?
Well, I don't know. I mean,
Immediately has to put in position of on the next level, right? There was a ref U1 before, and then you changed it to a elliptic function.
yeah, we can bring Katz-Moody later. So let's just. Yeah. And let's just then go through what I've written so far. Let's go through that same computation with this new so this is maybe easier to start with this one. So if I'm interested in what's the elliptic analog of this computation? Okay, maybe as much. Nikita, I may have to erase this table. Is that, yeah. Oh, okay. But there'll be some other pictures that somehow you can use. Yeah. So what's the analog of that? So if I want elliptic, maybe write first elliptic torus equivalent cohomology of a point. Well, if I have for U1, so if this is a product of U1 to some number R or N, if for U1 this is supposed to be an elliptic curve, well, it makes sense that this, of course, would be E1 e to the power R. So we're not talking about rings. We're talking about the objects that the corresponding rings define. So a ring is the ring of functions on some algebraic variety. That algebraic variety you can consider. This, if you take a non-affine algebraic variety, there'll be no ring of functions, there'll be sheaf of functions. But this is the algebraic variety. It's like this. This is that. And then elliptic covariant cohomology of null projective space. This is what? This is you take this guy here, cross one more elliptic curve. So this is you add one more variable. And inside here, so maybe this is some. So what does it mean? What does it mean I have take a quotient of a ring? That means the corresponding algebraic variety embeds the other way. So I have r copies of elliptic curve cross one more copy. And then said here, I look at the locuses where one, if I have coordinates ai here and the variable t here, I look at the locus as one of the ai's is equal to t inverse. Okay. This is, I use the equality and I use the inversion in elliptic curve. It's a group. I can not just or make sense? That's the locus in here. Yeah, they're all the same. Yeah, Q is always fixed. Yeah, elliptic curve is always fixed. And now you see that this thing is invariant. So there's an action of symmetric group, which is the Weyl group, of here. And so this locus is really descent, or it's a pullback inside. You look at unordered R tuples. So this is ordered R tuples, and you can consider unordered R tuples, cross one more of them. And so there will be the locus of the same, they're really the same equation. Defines it here. And this is naturally because this is, what's the difference between here and here? Here I have eigenvalues ordered, and here is eigenvalues go unordered. So this is the current UV current K theory of P. Yes. This definition, yeah. Well, definition is something else, but this is the result of computation. The computation is the same. Because what we used in the computation, what we really used in the computation, that if I have homogeneous space, so maybe I should say it. So now it's going to come rather close to Nikita's lectures, but maybe I will be a little sloppy in terms of identifying the exact nearest point. But Nikita maybe help me. So this is the how one way, if you're more familiar with Nikita's lectures, maybe one way to think about this is the following: so if I how how am I supposed to think of so maybe I'll look at, so let's just go back to that. What I was alleging here is that the UR equivalent elliptic homology of a point, that should be like the R-fold symmetric polarly elliptic curve. So it's unordered tuples of R point on the elliptic curve. You can say it's a definition, yeah. But anyhow. But you still want to think of this. You still want to think of an element here. It's kind of like an element in the group. So this is sort of like, there should be some kind of map from the element of the group to here. And what is this map? When I write an elliptic curve, so what's an elliptic curve? If I identify the unit circle with some, so I glue the unit circle to some, so if I glue the variable, the unit circle z equals 1, I glue to a variable. Usually people prefer to have q less than 1, so I do it the other way around. So if I have a q less than 1, so this is my variable q, and what I do is I glue the unit circle z equals 1 to the circle where the absolute value of z equals the absolute value of q, and identification is multiplication by q. That's the elliptic curve. And now if I have an element in the group G, I can form a vector bundle on the elliptic curve by saying, well, I'm just gonna I look at the sections of this vector bundle where the solutions of the equation f of qz equals g times maybe this element g times this element f of z. In other words, any element in the group defines me a bundle on elliptic curve. And this is clear, it's only up to conjugation. This is some kind of map from the group, or rather even classification of the group, to degree. So this is the degree of that bundle is 0 because the transition function is constant. So it's a degree 0 bundle. And so this set is really equal. These are semi-stable degree 0 bundle on E of RR, of semi-stable GLR bundles. This is for any group you can define something like this. For any group you can consider its classification, and you can consider the corresponding bundles on the elliptic curve, and then by using your group element as a transition function, and that would be like a map from the group to here.
Okay, I'm confused a little bit. No, that's a functions, only the functions, right? This is exactly what you are saying, right?
I'm saying what I'm saying, and you're saying something else. But so in Nikita's lectures, you've seen pictures like you go around. So I apologize. You kind of, I don't know if you've seen picture like you go around a circle, and you experience a monodromy G, right? This is the analog of that one dimension down, and then you also already had an elliptic thing, or yeah, there was also, but you know, in one dimension down for K theory, you can think of K. So in other words, so to make not to confuse people too much, just make some kind of connection, and we can talk about it. Make connection. What Nikita was explaining, that if I'm interested in K theory, recurrent K theory of X, there's some sort of relation between this and cohomology of maps from S1 to X. And but cohomology equivariant X mod G, but this is equivariant with respect to rotation. Rotation of Q is an element that rotates this S1. So Q here, you should think of an element of absolute value 1, and it rotates this S1. And in particular, what does mean you go to a quotient, and you closed loop may very well end not in your original point, but a point that changes by G. And similarly, if you go at one dimension up, and Nikita, I think I must have annoyed him by asking him questions about his lectures, but anyhow, you can one dimension up, the analog of that, you can have a situation, so you can have elliptic cohomology of X has something to do with the equivariant, again, with cohomology of now maps from actual elliptic curve to X mod G, where this elliptic curve is in the spirit of what we did here. Elliptic curve. Look, this is. I don't want to be precise about it. Yeah, I'm just saying that this is, you can interpret computations in this thing as computational elliptic cohomology, but you don't have to. It's much easier to work with what I've said, because here, elliptic curve can be any curve whatsoever. Like, for instance, it could be a curve or a finite field. I mean, you study cohomology with finite coefficients, no problem. If you have a finite coefficients over a finite field, you can have a very interesting elliptic curves. It somehow makes no difference whatsoever. Yeah, doesn't have to be presented in this way. Yes. Every elliptic curve is hyperelliptic.
Look at your fantastic central There is a ref at least 3 times. Ref. You need to put representations of something.
No, but this is what is rep. Rep is so your original. So okay, so this is your group modular conjugation. So okay, this to answer your question. What is your group modular conjugation? Group modular conjugation. So if I think of this object as bundles on elliptic curve, group modular conjugation are similar objects, but now when your elliptic curve is singular. Because if your elliptic curve is singular, just take P1 and glue 2 points. Then so the analog of that, this is like when Q is actually, so this corresponds to Q actually equals 0. Right? So elliptic curve is singular, then you have a bundle on P1, but you have to identify two endpoints. And this identification is a group element up to conjugation. So, and similarly, if you study bundles over nodal elliptic curve, those are naturally the Lie algebra of here. So if you think of it, what does it mean to define a bundle over nodal elliptic curve? That's naturally the Lie algebra of your group modular conjugation. Right, cuspidal, right. So this is the group, and this is the Lie algebra. This is nodal curve, yeah, and this is cuspidal, yeah. Well, if you think of it, so if I have a cuspidal cubic and ask what's peak of that? Peak of that are additive group of the field. Because so what does it mean? If I take the normalization, then the functions would be functions without linear term. And when you take modules over that, you can specify the linear term arbitrarily. This linear term in your function, that's what defines bundles. So this gives you, okay. So maybe I try to say if you think that the analog of group modular conjugation, so if bundles over nodal elliptic curve is group modular conjugation, then bundles over actual elliptic curve, that's kind of like elliptic analog of your group. So now to what? It's no. It's good. So this is a really good question. So what? So I'm hoping to get to this question later in this talk. So if there's somehow enough. So but before we we still need some general pieces of the story to put in place, and that's a general statement about Thom isomorphism. So if I have some space X, then I consider a vector bundle, some vector bundle. So maybe I need more space. So left. So I have some space. So I have some space X. Oh. Apologize. So let X be like that. And I consider some vector bundle V over X. So then so this is a complex vector bundle. All right. Then what Thom isomorphism says that if I take the Thom space from the embedding an X into this total space, space of vector bundles, vector bundle, that this is supposed to be the equivalent K theory of that is supposed to be isomorphic to, by Thom isomorphism, supposed to be isomorphic to equivalent K theory of the space itself. And you can imagine that and in fact, so what was the definition of that? These are the complexes of vector bundles on some neighborhood of X. So this is by definition. Complexes of vector bundles on a neighborhood of zero section that are exact away from the zero section. And we have a canonical element here, namely the Kazul complex. The Kazul complex is written completely in terms of a vector space. If I have a vector bundle, then I have the exact same thing, just fiber-wise. It's a complex that is exact away from the zero section. And the statement of Thom isomorphism is that, in fact, this guy is if I have a complex, you can tensor multiply it by anything you want, and this will still exact. And so then this guy is a generator.
This doesn't depend on C effect.
What?
It doesn't depend on which fiber bundle you take.
No, it depends. Depends. It's for every fiber bundle. So let me just say, maybe this is better to say is a rank 1 free module over Kx. And this is a generator. And using this generator, you can in principle identify the two spaces. And to say it slightly differently, you can consider there is an inclusion. So you can ask, there is an inclusion of the zero section. So there's a map iota inclusion of the zero section here. So you can ask, what's the pullback of this guy? So if I take the map K theory of the Thom space and map it pull back under the inclusion to the K theory of X, then the image of that goes into this Kazul complex times here. So this is maybe for reasons that I'm going to explain, I'll call it theta. So this would go into theta times K of X inside here. So this is not the Kazul complex. What's it going to be? The Kazul complex. You're gonna it's some complex. You pull it back, you get this expression. We have it somewhere on the board. Namely, this theta is the alternating sum minus 1 to the ith. Hold on one second. So this is the theta of V. I'm trying to motivate the good reason to call it theta. Right? So theta is just, so if I have a vector bundle, I can form this expression, which I want to call theta. And then this is the general feature of Thom isomorphism, and you can imagine how this goes. We did it for 1 point, but the argument was completely general. So if I have some bundle over some base, it's going to be the same. That this guy goes in here and it generates the ideal spanned by that theta. Right? And what is this? So this is this. Right? This guy here. And what is this guy? So like we did in the first lecture, any bundle whatsoever is pulled back from, so this is maybe a bundle, vector bundle of rank, let's say of rank R. And so this is back. This is a map to what? Map to the this B U R. So this is the Grassmannian of R-dimensional subspace and infinite dimensional space. Over that, there's a tautological bundle. And this class, so the bundle itself is pulled back, and the class, therefore, this theta of V, so maybe called, we had this gamma, and so this class theta of V is the pullback of this kind of universal theta, which is we essentially computed. That's the so if you think of this as this was the this universal thing is if you need to write. So what's a universal bundle of a Grassmannian? A universal bundle of a Grassmannian is just it's just kind of universal bundle with fiber CR. So this is if I think of xi's as the Chern classes of that or whatever ai's, so this is a product of 1 minus ai inverse. And it goes from 1 to r. This AIs are so this is so those are the Chern roots. These are the Chern roots of universal bundle. Well, because we want this is the reason. So if we want to express, if we want to normalize things so that the Kazul complex represents the resolution of the structure sheaf of the zero section, and that resolution goes in dual spaces, not. Okay. And now I now want to look at this formula and interpret it in terms of in the terms that we have there. So this is what, if I think of in general, this is what, this is the equation. This equation says that a matrix has a fixed vector. The matrix fixes a vector. If AIs are the eigenvalues of some matrix, as the equation says, the matrix fixes a vector. And then in terms of vector bundles on nodal curves, what does it mean a matrix? Matrix is a transition function that tells you how the section goes from here to there. What does it mean it fixes a vector? It means the corresponding bundle has a section. And the analog of that in elliptic homology is that you have a theta divisor inside R tuples of symmetric curve. This is given by saying that 1 this is one of the numbers is 0 or origin. And in terms of the corresponding bundle on the elliptic curve, it says this bundle has a section. This is kind of an important notion in integrable system. Many spaces in integrable system, they're moduli of bundles or something, somewhere, something. And then in moduli of bundles, we often have canonical divisors. Canonical, not in the sense that canonical divisors, they're distinguished divisors. That's formed by those objects that have an extra section. And that means some determinant vanishes or something like that. And that this is called the theta divisor in general. An example of that the theta divisor on the elliptic curve itself. That's the only, the 0. It's the only degree 0 bundle that has a section. And the theta divisors that was in Sam's lecture, those are formed by degree G minus 1 bundles that have a section. And in general, and if you have a particular section of that thing, which is usually given by some determinant or theta function or something, that's the tau function. So all I'm trying to say that if you want to define, there's an analog. So the moral of that story is that, not the moral of the story, it's an important point. The important point is that the elliptic analog of this story is in some ways similar, in some way not. It's similar in the way that there is a, so to speak, isomorphism for elliptic cohomology, which just says that if I study the elliptic analog of this object, this has become, so if I study in elliptic cohomology, this is still rank 1 module, which is not free, it's locally free. It's kind of an important thing. So it's not so we're talking about global objects, then it's okay to have things which are locally free but globally non-trivial. So it's a line bundle over that. And what is this line bundle? This Thom class is pulled back, so elliptic Thom class is pulled back of this class under the classifying line. Exact same thing. The main difference is that the Thom isomorphism is not an isomorphism. It's saying that some object is local, is a line bundle over, you have some things over some base, and locally it's isomorphism, but globally there's a non-trivial line bundle. And what does it mean concretely? So this says, so there's a, so if I, in other words, if I consider the corresponding pull-bell Mach in elliptic cohomology, that's going to be this will be, but no, just be saying, so what does it mean in K-theory? In K-theory it says there's this goes, so in K-theory that says, that goes to polynomials that vanish when this goes to the polynomials that vanish that one of the eigenvalues is 1, right? And that's same kind of thing, except the polynomials that vanish were one of, so what I'm trying to say. So I'm trying to say something very, very simple, but it's important. So if I look, so what does it mean concretely? Suppose I have a product of theta of AI. I goes from 1 to R, right? That's kind of like, that's a function that vanishes exactly when one of these variables is whatever, 1 or 0, depending how you denote the origin of the elliptic curve. But this is not a function. This is a section of a line bundle. And concretely, this is not if you, what does it mean? If you change the periods, if you shift AIs by Q, this will produce a non-trivial factor. So this is concrete manifestation of that. If you write formulas in elliptic cohomology, these formulas in general will have theta functions in them. But this is theta function is not a function. It's a section of a line bundle. And the meaning of that section, all these line bundles come eventually from the fact that this defines a locus where one of the things is 0. That's a non-trivial divisor in the product of elliptic curve. It defines a non-trivial line bundle. Make sense? So now that we have a Thom isomorphism, we can define So Kazul complexes looks like so this expression. So in theta functions you will have what's the theta function? Theta function looks like 1 minus say z inverse. Well, this is how Sam wrote it, something like that. And then product over n goes from 1 to infinity. You put 1 minus q to the n z, 1 minus q to the n z inverse, right? This sort of thing, right? And so this is you should. Very good. So this is so to speak kind of like the actual Kazul complex, and this looks like some sort of correction. But you think about it in terms of what I was trying to explain there. This looks like a Kazul complex on loops to X. Because if Q is what rotates a loop by some parameter, this looks like a Kazul complex. But it starts with this. And so this is the important part. This is what defines. So now we have to define push forward because this is so
excuse me. Do you hear me? I'm curious. Is that the divisor? The line bundle which determined by the theta divisor is just determined by the elliptic curve?
Maybe I can answer this question in 10 minutes because I need to really finish this topic. We need to somehow there's some curriculum we have to cover. So the Thom isomorphism, like I said, it's a wrong way map. So if I have some x that sits in some ambient y, and the normal bundle to y in x, if this is complex, it doesn't have to be holomorphic, it just has to have a complex structure. Then y, just because we can, Thom space is obtained by some sort of collapse. As we collapse, if we have more points in y, we can collapse those points. So y maps to the Thom space of x embedded into y. And so then we have that says that the K-theory of y, there's a wrong way map, the push forward map from the K-theory of x via the Thom isomorphism. This defines a wrong way map. So this is very easy to explain in terms of algebraic geometry. If X is a holomorphic submanifold inside a holomorphic manifold, then I can just take the structure sheaf and just push it forward. Just really embed. But this is, if you're interested up to some stuff, this can be said topologically. That's the way to say it. And this is a wrong way map. It has the property that if I push forward and pull back, that's multiplication by the Thom class. And so if I push it forward by Kazul complex, pull it back, then I just get the class of the Kazul complexes. And now if I have a general map is called complex oriented, if, so now suppose I have a general map. What? Oh, the normal bundle. That's right. Thank you. So general map from x to y is called complex oriented if I can take x, maybe this is y. What? Tom class. It's also this is the Tom class. This is Tom class. So if I have a general map called complex oriented, if I can realize it as an embedding like that, follows. So if I take some kind of bundle, might as well take trivial. So maybe I take a trivial bundle over y, and I want to embed x in a way just like I did into the trivial bundle. Then I take then by this kind of collapse, the Tom space of the embedding of y into this trivial bundle. Because no, y into the trivial bundle. So I embed y into a trivial bundle, and so this maps, because I can, if I want to collapse more, this maps to the Tom space of the embedding of x into its normal bundle. Right? Because what's a Tom space? Tom space is I take everything which is away from the zero sections and I collapse it all. Right? And so in particular, if I collapse the infinity of this space, I can collapse more and have this map. So this map, then the pullback under this is functorial. And by Tom isomorphism, this is kind of like K theory of y, and this is K theory of x. And they map the other way. So you have a push-forward map this way. But so this is, again, if we're talking about maps of algebraic variety, this is the definition of algebraic geometry. So what's it mean in algebraic geometry? Some map, you can embed your x into, I don't know, maybe projective space cross your target, and then you first push forward to that projective space, and then you push forward along the projective space. That's that. So for algebraic variety, it's the old definition. It just says for general things, for general maps, map is called complex oriented if it has a structure like that. Any two structures like that, you can, if you take the product of these two graphs, you can homotop one to another. So any two structures define the same map. So maybe I'll say this one point. It's kind of an important thing. In algebraic geometry, one can really push forward things. Just if I have a subvariety that defines me a coherent sheaf on the ambient space, and that's the push forward. And if I have a sheaf on some variety, and the variety maps to a point on some other variety, I can push forward that sheaf. And so this requires just really, but this you can say. To say this, it's enough to know just the Tom isomorphism. If you have this normal bundles that have complex structure, then you have this map. But then, so this is, if you unravel what this thing says, so if you unravel, if you denote so if this is my map, x goes to y, f. We divide the normal bundle to f to be the normal bundle to x in its embedding minus this Cn. And this is right. Again, if you really have a normal direction that you add, if you want to use Tom isomorphism one way, you multiply by theta. If you want to use Tom Thom isomorphism the other way, you divide by theta. Then the corresponding elliptic thing says that if I take the theta bundle of minus the normal bundle of F, and this is a sheaf on kind of elliptic homology of X, this maps to the structure sheaf of elliptic homology of Y. In other words, you don't go from functions to functions. There's a twist by theta functions, which is this. Because if you push forward one way, you multiply by theta functions. If you push forward, if you use Thom isomorphism, any use of Thom isomorphism means you have to multiply or divide by theta functions. And so this is, here you first use it one way and then in reverse, so you multiply by, by this you, by one part you multiply, by the other part you divide. Yeah, make sense?
Normally this shift on K elliptic of X later, right?
No. So there's some. This is elliptic homology of X. That's some scheme.
Yeah, scheme over E.
Scheme over whatever. Yeah. So this is on that scheme. I have a line bundle, and that maps there.
Normally with K, everything are schemes over E, not over some.
No. It could be over whatever. So over K crank homology of a point. Could be some whatever that base is.
But this means that K Thom is some red one shift over K of X, right? Local, right? But anyway, maybe.
Yeah.
So, good point to stop.
Let me. Yeah, maybe this is all I had. So there's many more things in my notes for today, but I think we're probably gonna get to them tomorrow.
Postpone them for tomorrow.
Yeah.
Okay. Questions. Actually, there was one unanswered question.
Yeah.
You pointed about trivial group.
Oh, right. So this is the So this is, we'll get to that in so this is what we're planning to get to that in so if I have homomorphisms of G1 to G2, homomorphisms of groups, then bundles, G1 bundles over E map to G2 bundles over E. That makes sense? So that is to say that elliptic G1 equivalent homology of a point, it's a scheme, maps to elliptic G1 homology. For instance, if if G1 is the trivial group, then its image is the trivial bundle. And morally, if I want to reduce the group, I just pull back things more. With cohomology, all operations cohomology you have to do in some cohomology of some complexes. So all this operation you have to do with some portion of derived pullback. But if you do suitably derived things, if you just pull back under this map, that's yours. So if you want to do non-equivalent cohomology, well, you have a trivial group. Non-equivalent cohomology means a trivial group. Whatever you had before, you pull it back. And as a preview, sorry, I apologize, a preview for tomorrow. Remember the equations for K-theory of projective point space? This was the equation was the product of 1 minus T inverse AI inverse equals 0, right? What does it mean to take it non-equivariantly? Non-equivariantly means set all the variables A to 1. And then you get just 1 minus T inverse raised to the dimension of the projective space equals 0, which is true equation for the case here of the projective space. Just because the generator is the same Kazul generator, the same Kazul complex, still the generator. It's just you forget the equivariance. Yeah. Do you have a question? Okay. Exactly, yeah. So this is so.
So when I make an elliptical molecule with that C star, I get less than C star. In the elliptical, less than C star. If I take the single group, I get more than the group. That's perfect.
No. This is so. Actually, you should think. No, this is not right. No. So the control question is you think they in. So okay. So maybe we'll take this kind of question. GL. Let's say. Stable or semi-stable GLN bundles over E, or in fact, on an anywhere curve, that's by Narasimha-Seshadri, right? That's the same as UN bundles over. Yeah, look, Vanya, we're in overtime right now. So what does it mean? This means for UN bundle, maybe so flat UN bundles. This means what? That means for a bundle we have this means maps from pi1 of E, which is Z square to UN, right? So this is the way we think of a. It's a kind of non-holomorphic way to think about elliptic curve is in fact as a pair of commuting elements. So similarly here, so you think of this, you can think of this kind of holomorphically or thinking non-holomorphically. Now if you think non-holomorphically, an element in elliptic homology is a pair of commuting elements. So for instance, if I take a cyclic group, pairs of commuting elements in a cyclic group, there's a n squared torsion point in elliptic curve.
Okay. So are you satisfied? So you already started tomorrow lecture, yes?
Yes, exactly. But
now it's a good point to take a break.
Yeah.
And the speaker. Now there are some other announcements from the.
Yes, please, let's take one more quick group photo with people who joined us this week and without people who left us this week. Okay, so it will be the same place on the stairs just outside the building and coffee break right after.
По-моему, про эллиптические космологии проективного пространства.
Да. Ну, в смысле, для тривиальной группы-то?
Да.
Ну, просто подставить там все А равняется единице. Вот и все. Да.
Когда ты говорил про длинное расслоение, я хочу прям на кривой на самом деле. Нет, у тебя на эллиптических космологиях точки есть линейное расслоение. На эллиптических космологиях. Да. Ну или вообще любое, так сказать, любое представление.
Потому что у меня, как сказать, нет. Глядя на вас, хочется пошутить, нет даже железной ноги.
Повыше или не слышно? Слышно? Слышно. Все. Да, ну я старался. А все сложнее? А, все лучше.
Просто так себе. К концу курса станешь человеком.
Что это за антиеврейская дискриминация вообще?
Okay, so it is time to continue.
Why so sad?
Wow, there is a lot of optimism in young eyes. So Professor Nekrasov is going to continue his course, and the rest you know better than me.
Actually, this is not what I meant to say. Sorry. Okay, so today we turn the page and introduce a new cast of characters, which will hopefully turn out to be the cast of all characters, and so eventually we'll reunite the second half of the course with the first half of the course. So to speed things up, I will make a jump. So what I'm going to talk about is supersymmetric gauge theory in 4, 5, 6 dimensions, but I will spare you the details and translate it to a class of statistical mechanical models, but I will skip the word mechanical. So we will be studying essentially probability measures or complexified probability measures. This is actually, I noticed that in this corner something happens. Okay, so measures on the set of multi partitions. So this way we'll make contact with several lectures at the school. For example, a lecture by Professor Schlossman, who just arrived. And also lecture by Sasha Veselov. And also, of course, lectures by Professor Kunkov. So these measures will depend on many parameters. And so it will take some time to introduce all the details. So I apologize. If you've never seen them, I'm sorry for you. But if you've seen them and you kind of get used to them, you learn to love them. So these are very interesting natural measures. Also related to the lecture by Grisha Alshansky yesterday, of course. Okay, so let me first. So what are the multi-partitions? So let's first let me remind you what are the partitions. So partitions are denoted by letter lambda, and they are there are many ways to think about them. So One is to say that this is a collection of non-negative integers. And so it is a partition. So in this way, this is a partition of an integer number, which is denoted usually as absolute value of lambda. It's called the size, and which is just the sum. And then the number of integers in the sequence is called the length. Oops. Now they can geometrically we can visualize them by drawing a diagram. It's called the Young diagram. So this is what you saw many times already. So it's a picture where now we introduce a collection of boxes. So the total number is equal to the size, and the number of rows, the number of boxes in the first row is lambda 1. The number of boxes in the second row is lambda 2, and so on. And we can coordinatize, so introduce labels to keep track of individual boxes. So my notations are flipped compared to Sasha's notation. So index I goes vertically, so I labels rows, and J labels columns. And so this is the box with coordinates ij. And so sometimes we'll write that the box belongs to lambda, meaning, and box is really just a pair of non-negative integers. And so saying that the box ij belongs to lambda is the same thing as to say that the integer j is between 1 and lambda I. And you can also flip, so do the reflection along the diagonal and get a Young diagram of a different partition, which is called lambda transposed. And this is defined by this relation. So the boxes of lambda and lambda transposed have coordinates which I just exchanged. So there is a finite number of partitions of given size, but of course, if we don't restrict the size, it's an infinite set. And it's a set which can be organized in a graph. So this is, okay, so this is called Young diagram. And just by looking at this picture, you can see that you can define some kind of a growth process where given the partition, given the Young diagram, you can attach a box to this diagram and produce another diagram, or you can remove a box. And so there is a procedure. So you start with nothing, and with to nothing you can attach just one box. So that's so the first two vertices of this graph, and then to one box you can attach a box to the right, or you can attach it from below, and then from here you can either continue this way, or you can go up here. And if you like, we can orient it. And so it continues indefinitely. So this is Young graph. So it's an infinite graph whose vertices are partitions, and two partitions are connected by an edge if there is a way to obtain one from another by adding or removing a box. And if you want to know your options given the partition, so this is partition lambda. So if I'm already sitting somewhere in Young graph, and I want to know where can I go from here, so by looking at the diagram, I see that there is a certain number of corners where I can attach a box. And so the collection of these boxes I will call the positive boundary of lambda. And there is a certain number of boxes which can be removed. And so this will be called the negative boundary of lambda. And we can compute the number. I mean, the cardinalities of these two sets can be pretty random, but there is an index, there is a topological invariant, which says that the number of positive boundary minus negative boundary boxes differ exactly by 1. So if you just start from here, these two match, these two match, these two match, and then this one is not matched. Now there is a further way of kind of capturing the information about the shape of the diagram, and that's a character of the diagram, which I will also denote sometimes as chi lambda of two indeterminates Q1 and Q2, and this is just the sum over the boxes in the diagram, Q1 to the power I minus 1, Q2 to the power j minus 1. So if you are given this function, you can reconstruct the partition and vice versa. It's a definition, yes. Well, it is also a theorem, but yes, very, very good. It's to formulate the theorem, I need to give you yet another definition of what partitions are, and so this definition becomes kind of meaningful if we identify lambdas partitions with the set of monomial ideals in the ring of polynomials in two variables of finite codimension, so of codimension absolute value of lambda. So from the lectures of Andre, you know everything there is to know about this ring, and so today he was explaining to you what does it mean to sit at the origin. By what's the Cazul resolution of the skyscraper shift at the origin, and it was actually perfectly illustrated by the attempt of the chairman to stop the talk. So if you want to fix the moment in space and time in algebraic geometry, you cannot just say that I'm going to sit here. You have to say that I'm sitting here, but if I make a step, I will be multiplied by the function which vanishes at this in this direction, and if I make that step. And so this is dance of the resolution, and that's what we're going to do now to understand these boundaries. So what's the monomial ideal? Monomial ideal is the ideal which is generated by monomials. So it means that for some integers I, a and b, and the requirement that it is of finite codimension. So it has several generators. So there are several generators. So I goes from 1 to, I don't know, there is some number of generators. And so to understand what it takes to make the ideal of finite codimension, we need to, okay, now I need to borrow the picture from Andre's talk, and so draw it again, except that I will change the notation from x to z. And we will achieve x to z by doing this, of course. So this is the monomial 1, and this is the monomial z1, and this is monomial z2, z1 squared, and this is z2, and so on. And so I apologize, I lack the patience to draw a more realistic ideal, but whatever. So if you have an ideal which is, if you have a monomial which is in this ideal, so somewhere here, z1 to the power a, z2 to the power b, then everything which is to the right and above of it will be in the ideal by definition. So ideal is what is invariant under the multiplication by polynomials. So if this is an ideal, then any monomial multiplying it will be also an ideal. So if you have some set of generators, they will cut out certain portion of this positive quadrant. And now if I want the complement to the shaded region to be finite, then it means that it has to come up here somewhere. It has to come up here somewhere. And so if you draw this boundary, you will see something which looks like a Young diagram, except that it is flipped upside down. So that means that among those AI, BIs, there must be one where B is 0, and there must be one when A is 0. So that, but now more importantly, if you look at this picture, you see now what is the meaning of the blue boxes. So the blue boxes are these guys. So this is, okay, so the monomial ideal is actually generated by, okay, if I'm, so it is generated by monomials of this form when I goes from 1 to the length of the partition. And so the boxes in the outer boundary are precisely the generators of I lambda. So Young diagram itself represents the quotient. So the Young diagram so the expressions, the monomials of the form z1 to the power I minus 1, z2 to the power j minus 1, when I and j belong to the partition, they, if you like, they can be chosen as a basis of the quotient space, and that's the space which let me call it K sub lambda, and this finite dimensional by the requirement of the codimension being the size of lambda. So so the maximal value given I, j can achieve is lambda I, and so if I make this so the exponent make it one higher, then I'm already inside the ideal, and that's in fact a generator. And so these are the generators. Now, actually, the actual number of blue boxes is smaller than, could be smaller than the list here, because this is a It's exhaustive list, but it's not minimal. So the blue boxes are a minimal set of generators. What I mean by what I just said was that in this list, there is a box in this, there is this box, which is not needed as far as the ideal is concerned, because this is already in the, is generated by this blue guy. Now, what about the red guys? Well, usually, so these are generators. Okay, I see. These are, so there are generators, but there are also relations. So if you look at this box here, it is it can be obtained by multiplying this blue box by some power of z1, and it can also be obtained by multiplying this monomial by some power of z2. So there's a relation in this ideal which connects things which are generated by different generators. And so these corner boxes, which I denote there in the red, are in one-to-one correspondence with these relations. And so bottom line is that delta plus corresponds to generators of the monomial ideal associated with lambda, and delta minus are associated with the relations. So now, to make this well, not exactly that. So yes. So that's what I said. I said one-to-one correspondence. So there's one-to-one correspondence with this box and that box. I just I like to historically, just it's happened historically, is that if you like Young diagrams and you think about how they change, so these are the boxes you care about, because this is what you remove, this is what you add. But in the formulas which we will be dealing with, we actually deal with those boxes which are always outside. But these ones are related by just shift by Q1, Q2. So now another way of saying what is to be a monomial, does it mean to be a monomial ideal? It means that it is invariant under the C star cross C star action, which rotates Z1 and Z2. So, and therefore, this quotient space becomes a representation of this two-dimensional torus. And this character is the character of C star cross C star action on K lambda. So this is a theorem now. The theorem which is proven by just direct observation of this picture. So the monomial which sits here is the eigenfunction of this torus with the eigenvalue t1 to the power of I minus 1, t2 to the power of j minus 1. And I chose letters q1 and q2 instead of t1 and t2 to confuse Vanya. So that's my, all right, but what about these generators and relations, and what's is there a way of somehow enumerating, keeping track of these blue and red boxes? It turns out, yes, there is a way to sorry, could you say it louder? So this vector space, K sub lambda, it's a vector space. which is a representation of this two-dimensional torus. Not every space is representation of it. No, I mean, okay, so if, yes, as a abelian group, representation splits into sum of one-dimensional representations. But not every ideal in the ring of polynomials will lead to a representation of the torus. Because if you take the ideal generated by, let's say, Z1 to 5 plus Z2 and Z2 cube, for example, it will not be invariant on the direction of the torus. So in fact, the torus will move it to another ideal. And so if you think about the space of all ideals, the torus acts on the space of all ideals, but some of them are invariant. And so these are precisely I lambdas. This is not monomial, and which is the same thing. It's synonymous to not being torus invariant. Okay, so now I need to introduce another quantity which is related to chi, which is 1 minus which I claim it is precisely the sum of so this virtual character keeps track of the sorry, I should have used the colors. So this is from the colorblind days. Where I use the notation for the content. So this is the refined version of the content used by Sasha Veselov. So the content of the box, ij, is a linear function of I and j with slopes log q1, log q2. And so I claim that knowing the character of the partition by doing this algebraic manipulation, you'll extract two characters, so one with the plus sign, one with the minus sign, and those will give you precisely those blue and red boxes. And that's essentially just repeating what I said about the generators and relations. So you already know this, actually. You have seen this an hour ago. So this is essentially the calculation of Kazul resolution, but with at the level of characters. So so there is one. So suppose lambda was empty, for example, nothing. So then S lambda is equal to 1. And that's just the fact that for empty partition, there is one box which you can add. And that's one, which is here. So it's easy to understand what is the ratio of S lambda divided by 1 minus Q1, 1 minus Q2. Well, this is just the sum of all ij such that z1 to the I minus 1, z2 to the j minus 1 belongs to the ideal of q1 minus 1, q2 to the j minus 1. Why is that? Well, what did I do? I just computed. So I took this quantity, which is just the sum of over all positive monomials. And then I subtracted chi lambda, which is the sum over all monomials which are inside my Young diagram. So the remaining monomials here are precisely the ones which were in the ideal. Now let me try to represent this ideal in terms of generators and relations. So every generator spans a cone. I think it's a cone in your sense, right? You had cones, right? Yes. So there is a cone. So for every blue box, I draw. So let me draw it like this. So this is the sum over blue boxes. So every blue box, spawns children. So these children are the monomials which are divisible by this box. And so this is the sum is the character of all monomials which are spawned by the generators. But in the actual ideal, I've counted certain monomials more than once. So there are children which are shared, kind of joint custody. So so everything which is here is already accounted for by the descendants of this monomial and descendants of this monomial. So I'm subtracting them. Say it again? Yeah, so, well, no, there are of course custody battles because some can be claimed by many parents, but if I do kind of start from here and subtract one by one, then it comes to a peaceful resolution eventually. So, and so there is a factor of Q1, Q2 precisely because of what Senya observed, that I'm looking at the internal corners and they are related by a shift to the ones outside. Okay, so this is clear. So now there is a little bit of homological algebra. So this is some identity on characters, but there is also what's now called categorification. So there is a complex, actually maybe tautological complex, associated to the partition lambda, and that's a complex I should put here space Q and here space lambda of Q, where Q is C2, and I always make this mistake. It is probably the dual space to the space on which my polynomials are functions. Maybe not. So what is this? So this is map sigma and tau, or like differential d1 and d2, and so d1 takes a representative of the of this quotient space, and multiplies it by the coordinates. So z1 k, z2 k, and projects down to the quotient and puts 0 in here. And G2 takes the triple k1, k2, and the number u, and sends it to I guess u plus z2 k1 minus z1 k2. Right. So so it is easy to check that the composition is equal to 0. And I mean, if you were careful, if you watched Andre carefully, this part is part of the Koszul complex. Because it's essentially it's a multiplication by a vector, and then external multiplication. Follow the definitions. Let's not worry about it. So, well, see, so this is, what do you mean? It appears here. So it's part of this map. Well, now the question is, what is the cohomology? So this complex has interesting cohomology, and this cohomology is trivial in degree 2, and it's non-trivial in degrees 1 and 0. And so the claim is that this is precisely the character of the first cohomology of this complex, and this is the character of the zero cohomology of this complex. No, character. So a character is a representation of the torus. This complex is the important thing is that this is C star cross C star equivariant. So every term in this complex is a representation of the torus. Here I take the trivial representation, and the map is equivariant. So see, Q is taken to be it's a defining representation of this torus. So yes, what's the question? And because it's equivariant, the cohomology will also be representations of the torus. And so that's the sorry, not this. It's not what I meant. This is what I meant. This is actually the cohomology, the character of the, okay, maybe character of H1. And this is the character of H0. Well, think about it. What is, let's do it on this picture. So what is the cohomology in degree 0? So this is just the kernel of D1. It's just the kernel of D1. So what is the kernel of D1? Well, these are the elements of the space of my quotient space. That is to say, some linear combinations of the boxes, which vanish when you multiply them both either by which vanish when you multiply them by Z1 and vanish when you multiply them by Z2. Vanish in the quotient space. And so how does Z1 and Z2 act? Well, multiplication by Z1 simply shifts you one position down, and multiplication by Z2 shifts you one position to the right. So this box here, for example, vanishes when you multiply it by Z2, but doesn't vanish when you multiply it by Z1. But these red ones, they have nowhere to go. Sorry, what do you mean? You mean to move the picture, or you want? Okay. So I just shown that the kernel of the differential D1 is precisely spanned by the vectors corresponding to the red boxes. And so that's and so this is the character of H0. I'm not sure about my shift by Q1, Q2, but okay. And it is a little bit less obvious, but I invite you to check that this character, you see, when I computed this quantity for you, I called it a virtual character. It's not a character of a vector space, because some exponents come with plus sign, and some exponents come with minus sign. But it's a virtual representation of the torus, and it is a difference of two actual representations of the torus. And now I've presented to you what are these representations. This is H1 and this is H0. And the fact that there is no cohomology in degree 2 is a cute exercise in Lagrange interpolation formula. Also known as discrete differences. Yes. I apologize. Okay, so now that we've somewhat familiarized ourselves with partitions, I can hit you with multi-partitions. You know, we are told that we should live on multiple planes of reality, and so the good object to study is not one. I mean, you can have a lot of fun just working on a set of just partitions, but for we will need multi-set. So now I have to multi-partition. It's just a collection of partitions. And alpha will be will belong to some finite set, which we will specify later. Okay, now the measures. So what are the measures? So ultimately what we want to do, we want to compute some kind of partition function, which will be the sum over the multi-set of partitions. And so there will be a measure which depends on the shape of these partitions and will depend on some parameters. Typically there will be some set A. So now there are three theories. So cohomological, K-theoretic, and elliptic. And the only difference is that so in cohomological theory you use rational functions, in K-theory you use trigonometric functions, in elliptic theory you use elliptic functions, and there are limits reducing elliptic theory to anything below. So I can write formulas maybe in elliptic category to begin with. So in physics language, this would correspond to the 4-dimensional, 5-dimensional compactified on a circle, and 6-dimensional theory compactified on elliptic curve. You're not okay. So to motivate, well, there are, I mean, the origin of these measures is the so from localization in elliptic homology of some moduli spaces. And these are modular spaces of solutions to some partial differential equations. The equations are defined on R4. And so this R4 plus the 2 dimensions of the elliptic curve, they make this 6. And if you do K theory, there is a hidden circle there, and that gives you 5. Right. Well, you see, the cohomology theories are associated with groups, and so you need a group law. And if you classify possible group laws, the elliptic curve is where the buck stops. Which doesn't mean that we cannot have 6-dimensional theory compactified on the high-genus Riemann surface. It's just that the genus of the Riemann surface will be encoded in the set A. So, okay, so I promised you a bag of tricks. I have many tricks. It's just that I'm giving you. I'm just I'm taking some. Only one pile of them. But indeed, there are mu's associated with higher genus surfaces, but they expressed in terms of the rational function. So they only admit a cohomological treatment. So there is no even K-theoretic version of it, as far as I know. Okay, so I did not explain it. No, I did not explain. Yeah. No, it's just that this curve is not the curve which encodes the type of the measure. It's the curve encodes the type of the set A. I did not explain. I mean, I didn't write a single formula yet for. So mu. So what? I mean, there is a lot of details in the set of indices here, and what kind of measure is there, and so. Okay, the question. So the formulas tend to be pretty long. So maybe it's easier to start with a simple example and then go up in complexity. So let me start with an example where my set A will be just the set of integers from 1 to n, and they will be treated on equal footing, so I call them colors. And so my measure in this case will, so the parameters, so this example is called A0 hat example. So the parameters are the collection of complex numbers So this n is this, and 3 additional complex numbers, which I will actually make into 4, but require that they sum to 0. And the last parameter, q, which I will denote by q slash, so as not to confuse it with q1 and q2, and it's going to be the elliptic curve parameter, although it is not obvious from the outside that there is any relation to elliptic curve here. So this is I'll denote it by e to 2 pi tau, and so tau. So these are my parameters, and so the measure in this case okay, so there will be first of all just a sum of all sizes. So once again, the random variables are just a collection of n partitions. Now, I need to look into my notes. All right, so we have the product over ij in lambda beta. So my product is over pairs of indices alpha and beta, but here I'm taking the product over boxes in only one of the two diagrams, which I can associate to this thing. But in the contribution of this box knows about the other diagram. And I can put here the theta function. And theta function will, so when I write theta of x, depending on whether I'm in cohomological K-theoretic or elliptic theory, this could be x, it could be 1 to the minus e to the minus x, or it could be the product 1 to infinity, 1 minus p slash n minus 1 e to the minus x, 1 minus p to the n e to the x. So the elliptic theory depends on its own, on another parameter p, which is the so this is another elliptic curve which has nothing to do with this elliptic curve. Okay. And so I don't even count it in my parameters because it's just part of the kind of ground field. All right, and okay, now so I should have written this in a smarter way. It's the product ij epsilon 3 plus the same thing. Times, unfortunately, I have to go to this board, product over ij of the diagram alpha, and there is something like the conjugation going on here. So it's lambda j alpha. Sorry, this is lambda transpose. So one thing which you can always remember, so lambdas have index I and lambda transpose have index j. So that's my bookkeeping. Right. So So transposed 1 minus I plus epsilon 2 j minus lambda beta I. And here's plus the same thing. Okay, so it looks pretty terrible, but it is actually not that bad. There is a way to understand this. So let's first so in this product there are terms when alpha is equal to beta. So in this case, so if alpha is equal to beta, then the quantities which appear here have a name. So if I'm sitting at the box ij, then so lambda I is the number of boxes in this row. So the quantity lambda I minus j is the number of boxes to the right of that box. It is called the arm. It's called the arm. And similarly, there is the number of boxes in this column is lambda j transposed. And so this quantity lambda j transposed minus I is called the leg of the box ij. So what we have here are the generalized arms and legs. So this is arm plus 1, and this is minus leg. Except that for general, so if I have a pair of diagrams, I can actually define the arm and leg of the box of one diagram relative to another diagram. And so sometimes this quantity can be negative. Now, there's a special case of these measures. So this is what happens when alpha is not equal to beta, right? So for example, this is alpha, this is lambda alpha, and this is lambda beta. So then typically you will have both positive and negative expressions. You may also get 0, but when alpha is equal to beta, you never get 0. Oh, I'm sorry. Most important thing, my parameter is a. So everywhere I should add a alpha minus a beta. A alpha. Otherwise you might get 0 in denominator. And here the claim is that for theorem, if you like. Is there interaction between what? Yes, you see, it's a I have lambda beta, lambda alpha. A alpha minus a beta. So no, of course they interact. So one way which Young diagrams have not been presented here, I think, yet. Did you have this picture? Not yet. So. No? Okay. So one way to think about this ensemble is that you have diagrams. So Young diagram, if I rotate it by 135 degrees, it will look like now I call it a pile of bricks thrown into the cart, or the gardening cart. which grow over points A1, AN, and these points are actually complex. So think of this as a complex line. Say it again. Well, it's my drawing is bad. Yeah. So I mean, these are rectangular bricks. Sorry. And in some sense, the sizes of the sides are epsilon1 and epsilon2. Okay. And it should be epsilon1, epsilon2, but sometimes it looks like it's epsilon1 minus epsilon2. It's actually complex, yes. So actually what happens is that on the complex plane, you have a growth process which start with seeds at the points A1, AN, and the growth is with steps epsilon1 and epsilon2. So these are points, so this is A1 plus epsilon1, A1 plus 2 epsilon1, A1 plus epsilon2, A1 plus epsilon1 plus epsilon2. And the diagram, Young diagram, is just the boundary of this process. Maybe I should have, sorry. The boundary is somewhat outside. And so this, and these boundaries somehow interact. So there is some kind of a potential. So there is some sort of potential between, which sort of attracts or repels the corner boxes which we discussed earlier. So the blue ones and the red ones. So this is some kind of dipoles. Some kind of dipole. Interaction. So it's a discrete process. So my charges are allowed to occupy only certain positions. But if you decipher this point, you get something like Coulomb gas actually, but Coulomb gas of dipoles. Now, there is, of course, a simplest case. So this formula makes sense, makes perfect sense for n equals to 1. So if n equals to 1, we can simplify. So there are no a's in this case. So then we'll have just the sum over a single Young diagram, q to the power lambda, and then the product over boxes in a single box. So then we'll just have theta of epsilon 1 minus leg of the box plus epsilon 2 arm plus 1, epsilon 1 leg plus 1 minus epsilon 2 arm. Now, yes, epsilon 3 is called adjoint mass for the initiated. And so is epsilon 4, which is negative epsilon 1 plus epsilon 3. So there is a symmetry. It's not obvious, but there is a symmetry which exchanges. So there are interesting symmetries of this expression. You can exchange epsilon 1, epsilon 2. You can exchange epsilon 3 with epsilon 4. The epsilon 4 is defined through this relation. Now, remarkably, this can be summed up. I will not bother you with the formula for the elliptic case, even for k-theoretic case. Let me. So in the rational case, when theta is just its argument, this is summed up to the remarkably simple formula. So this is the denominator which you saw in Senya's talk. So this is one of the so if epsilon 3 were equal to 0, this is the conspiracy of this formula. If epsilon 3 is equal to 0, then there is a complete cancellation. And so it becomes just a uniform measure, and then you're just counting partitions with the weight by their size. So this is what you would have gotten, and that's the famous Euler computation reproduced by Professor Schlossmann a couple of days ago. But if epsilon 1, epsilon 2, epsilon 3 are non-zero, then it turns out it's not very much different. It's probably minus 1. So it's just the complex power. What do you mean? Only an exponent, yes. Only an exponent. And so there is a, by the way, what's my time constraint? Okay. So, okay, so there is an interesting story about this formula. So there is a special case. This is the full formula. This is n equals 1, so it's not the interesting, not the most interesting case. But okay, maybe I should not spend too much time on it. But just so there is a special case which is related to the representation theory of symmetric group. So this is in this case, this measure, let's say epsilon 3 goes to infinity, and q goes to 0, so that epsilon 3 squared q is fixed. So okay. limits, interesting limits. So then this measure simplifies, and it becomes the Plancherel measure studied by Vershik and Kerov. So this is the famous Hooke formula. So this is the product over the boxes of 1 over the Hooke length squared. So what is the Hooke? The Hooke is the arm plus the leg plus 1. And so if you don't take the limit epsilon 3, so they studied, yeah, I mean they were interested in what's called the microcanonical ensemble, where they fix the size of Young diagram and send it to infinity, right? So we work. So in physics, there are two sometimes equivalent approaches. You can work in the canonical ensemble, in the ground canonical ensemble, where you don't fix the size, but you fix the fugacity. And then sending the size to infinity corresponds to taking the limit when the fugacity goes to infinity. And so it's equivalent. So you can get the limit shape from that. Yes, so one of the stories of this whole, I don't know, tale or ballad is the study of the asymptotics of these measures when the parameters epsilon1 and epsilon2 or epsilon2 go to 0. So and that's the story of limit shapes. So limit shape in this language would be when you send epsilon1 to 0, keeping lambda fixed. So more generally, sorry. Yes.
I was afraid you're going to erase this photo.
No.
Something I wanted to say.
Yes, please.
So this is relate to rigidity of Cauchy-Euler generally. What the Sida function oracle said says that the Cauchy-Euler genus of the Hilbert scheme of points equals the orbifold Cauchy-Euler genus
Of the symmetric product. Right. Yeah. So this is something like the elliptic genus of C2. Not elliptic genus, but like this, like homological expression. So if you do it in elliptic homology, what is trivial is doesn't look trivial on the blackboard. It's something like a platistic exponent, which is what symmetric product does. Yeah, it's okay. For the experts, let me explain. So this is we're not alone. So we think that we live in R4, which is C2, but it's not just C2. It's a C2 which sits inside C4. And so you see, I have 4 parameters: epsilon1, epsilon2, epsilon3, epsilon4. So there is a 4-dimensional space hiding in this story, and our C2 is just a sliver of the reality, just a 2-dimensional plane inside a 4-dimensional space on which acts a 3-dimensional torus. 3-dimensional because I have a constraint, and so this is the. So it's a 3-dimensional torus. It's a torus of SL4. So it's something which preserves the volume form. And so it's C2, which is kind of abstracted. It's C2 with a bundle, precisely bundle over it, 2-dimensional bundle, and the epsilon3, epsilon4 are the weights of this bundle. Okay, so to make contact with Stas' lecture. Okay, I did not explain much. So this is what Andrei said was that this is actually an integral sum over n, 0 to infinity, q to the n, and then there is an integral in the sense of elliptic homology integral, elliptic over the Hilbert scheme of n points on C2 of the equivariant. Well, equivalent Euler class or Chern. So what would it be? It would be like okay. In the language that Andrei was using, it's the integral of the wedge of exterior algebra of the cotangent bundle. And so this is, of course, so it's -1 to the I. And yeah. So if you didn't put here anything, and if you remember his lecture, that means that you are taking the cotangent bundle, and then you look at the zero section and look for the zeros of a generic section. So it's like Euler characteristics. But we want to make our life more interesting, so we weight these factors not with -1, but with e to the I don't know, -1 to the e to the q3 to the power I. So q3 is e to the epsilon 3. And now you can ask, how come I've broken the symmetry between 3 and 4? But because of the symplectic nature of, because it's a symplectic manifold, well, you can check from this formula that actually you can exchange it from 3 and epsilon 4.
So if we did 3 and 4 are because of measure of the cells, corresponding to Young diagram. Right? I'm just trying to clarify the nation of A, epsilon 3, and epsilon 4. Is it because of star, T star, rotating bundle?
Yes, yes, it's because of T star. Yeah, it's because of T star. Well, okay. This is okay. T star is actually an effective description for something more profound, but it's for the purposes of this calculation, it's because of T star. So the way I wrote it here, this is this works already in elliptic homology. So this is, think of this as a class in elliptic homology. So
Your original status formula was without T star. Simply count the measure of the cells, corresponding cells, which are given to arms and legs, right?
no, this is, you see, this is the denominator. So denominator comes from the tangent space to the Hilbert scheme itself. And then the numerator comes from whatever class you want to integrate over it. So no, it was an original formula. It was an original. Okay, so to make okay, so for general n, life is not so simple. In fact, already for n equals to 2, and right, for n equals to 2, this partition function already describes conformal blocks of 2D CFT on an elliptic curve with parameter q with one puncture. So if Stas were to do what he was doing yesterday on the two-dimensional torus as opposed to a domain, and he had a specific defect inserted there, and he took a continuous limit, and then he managed to factorize it into the product of holomorphic and anti-holomorphic objects. The holomorphic object would turn out to be, I'm sorry, I erased half of that, but okay. How to what? Yeah, you have pairs of Young diagrams. Pairs of Young diagrams. N equals 2 means pairs. Liouville. Okay, since I have only like 1 minute left, yes. Right. So as yesterday was explained, everything is related to everything. So pairs of Young diagrams are related to representation theory of GL2 hat. And inside the GL2 hat, there is SL2 hat. And there is Drinfeld-Sokolov, which gives you Virasor out of SL2 hat, which is the symmetry of the Liouville theory. So this is, I mean, it's roughly the explanation. Okay. So there is a part which, so one Young diagram is almost trivial because it corresponds to just a free boson. And so that's why this is to Liouville. Liouville plus free boson, actually. So we need to decouple these factors. Okay, so tomorrow we'll introduce a new tool for studying these partition functions and studying expectation values there, and this new tool is called the QQ character. So there will be no what? No, this is too simple. No, forget about that. So what do you want? No, it's a new special function. It's a conformal block of Liouville theory. It's a special function. I mean, when Q goes to 0, it reduces to hypergeometric functions, and then you can expand it to hypergeometric functions. But okay, sometimes, okay, since I have parameters, I can play with parameters. Sometimes, if there are some rational relations between epsilons or a's, things can simplify. So sometimes you get hypergeometric functions just without taking limits. I want to finish by saying that okay, you may worry that I have things in denominator, and things in denominator sometimes vanish, and sometimes you get poles. So the poles are when A alpha minus A beta plus epsilon 1 times. So poles at when I and j are both greater than 1. But sometimes these poles are not so bad. So they are, sorry, what do
You mean that some of them actually cancel?
sometimes they cancel, right? So, for example, if epsilon 1 over, so if the ratio of epsilon 1 to epsilon 2 is a positive rational number, then the individual contributions will have poles. It will be poles, but they cancel. So, and that has to do with the fact that the fixed point set in the modular space, for example, in the Hubble scheme of points, is not isolated. No, that's not. This is not the way I put it. No, that's not the way I put it. But compact. And if you have a pole when A's are involved, then it's this fixed point set is non-compact, and you have an actual singularity, actual pole. Okay, so let's stop for now.
So you just.
I'm finished. I have. Oh, okay.
Oh, there is five
Oh,
minutes,
sorry,
but so at least
sorry,
you can
I misunderstood your.
You can no less than 10 minutes, but it's still
Okay.
you should at least make some maybe conclusion, some maybe fix what you said, because
Okay. So
some people I believe are lost.
all right. So what are we trying to achieve here? So we are. So we are. So I've defined. I didn't explain where I got it from, but I defined some measure, which I can normalize on the set of multi-partitions, and we want to study expectation values of some observables. So by definition. So all evaluated on lambda. So and the claim is that there are observables so observables are just functions on this set of multi-partitions, some functions of set of multi-partitions, for which expectation values solve interesting equations. And so equations are Knižnik-Zamolodchikov equation,
For which current algebra?
Pilavin, Polyakov, Zamolodchikov. It all depends on the choice of observable. So it's a clever. It's a game. So I give you observable, then you prove that it solves this equation. So BPZ for Virasoro, and now people pushed it to W3, maybe WN. Spin chains. So they could be wave functions of spin chains. Of ADE spin chains. And also ADE hat. And the partition function itself, so Z, as a function of epsilon 1, epsilon 2, if you take the limit when both epsilon 1 and epsilon 2 go to 0, has the, with the proper normalization, has the asymptotics, which, so this leading singularity depends on epsilon 3, q, whatever parameters are left, and this is the prepotential of some special Kähler geometry. Special Kähler is one word. I mean, it's not a geometry, also known as Darby-Bruton geometry. And so quite often there is a family of curves with Krichyver data which capture these asymptotics. So it's and the asymptotics at the level of these Young diagrams corresponds to the limit shape problem. So it's a generalization, kind of vast generalization of Vershik-Kerov problem. And also there are other interesting limits when epsilon 2 goes to 0 and epsilon 1 is fixed. So this partition function still keeps surprising. So there's an interesting asymptotics with less singularity. So it has now additional parameter. And so that describes, well, in a sense, it describes the deformation of special geometry, and you can call it quantization. And sometimes it is quantization, and sometimes it's a classical geometry, but in a rotated complex structure. So let's discuss it in more detail. This is a famous Cherednik mistake. It's a twisted superpotential.
Okay. Okay. So that.
Yes.
That was
celebrated.
That was an announcement for
yes.
2 other lectures. Yeah.
Yes.
One of which is kind of a half a year course.
Yeah.
Okay.
No, we will not go through all of that. Our goal is
I believe, yes.
Our goal is to connect to specifically elliptical Algera-Mozart system.
I see.
Or maybe number of particles. For n, for capital N, the measure which I described with this ace, with n ace, describes the quantization and deformation of elliptical Algera-Mozart system with n particles. N is n.
No, there is.
Yes.
There is elliptical Algera-Mozart because there is an elliptic curve. On the blackboard
the
there is nothing.
Is
just
governed
nothing.
by the
just
parameter
nothing.
q. It's by the elliptic curve parameter. Because these measures, they
which
are
is different from a previous
small
lecture.
deformations of uniform measure. So the series is kind of dominated by the uniform measure, which is just the nth power of the Dedekind function. Yes, oh my God! Yes. It turns out that elliptical Algera-Mozart is actually related to the A0 hat spin chain.
And it's for theta not being elliptic, yeah? Not
yeah, it's a rational case. For the rational
it's for rational theta.
So in this famous exchange of letters with you, you wrote a formula for general beta ansatz for general Cartan matrix, but I don't think at the time you knew that you could also put affine Cartan matrix there. It's so yes, because it actually requires an extra parameter. Epsilon 3 is a parameter which only appears once the Dynkin diagram of the corresponding algebra has non-trivial pi1 as a loop. And so it's the additional piece. Loop pi1 has a fundamental group. The Dynkin diagram is not simply connected. H1. H1. Okay. Okay. No, but of course, but it could be. Yeah. Okay. So it corresponds to H1. It's H1, of course, of course. Maybe Vanya will generalize it to non-abelian parameter. Maybe there is a non-abelian epsilon parameter. So then, for for the monster algebras, maybe it will be a non-abelian extension. What do you call the algebras which correspond to multiple loops? Hyperhyperbolic, ultra hyperbolic. Okay.
Okay.
Yes. Yeah, so it's most likely yes, most likely, but I cannot prove it. I don't have I lack. All the parameters are there. Yes. So so Q1, which is e to the epsilon 1, and Q2, which is e to the epsilon 2, are Q and T inverse parameters of the Macdonald's, for example, if you like.
Okay. So if no more question, finish the morning session and come back. What time? At 2 o'clock.
just take it on and remain.
А коврик ты был неправ,
It is now on.
No, it's on. Okay.
отлично влез.
Probably better.
Самое не перегородить. Все супер. А цена, я бы сказал, такое. А нет, он мне покупал по замечательной системе. Интернет.
It's starting. Okay, welcome back to the afternoon session. The last one, actually, right, of the 2 weeks. The last afternoon session, because tomorrow it will be open. Tomorrow's a movie, so the last academic one. Okay, cool. Welcome back. We'll have Dajun Zhang, okay, from Shanghai, talking about elliptic solutions related to the Lamé functions. Welcome.
Okay. So maybe first I would like to thank the organizer for organizing this such a wonderful workshop. So do you need to turn off the light or something? Turn off the light. Okay. So yeah. Sorry. Okay, I should say something about Professor Creature. I would say Professor Creature because I have only very tiny overlap with him. That was in 2009 in Newton Institute. There was a half-year program on fully discrete integral systems. So I was there in a short period, and I think I have maybe just a few days with this Professor Creature. But unfortunately, I didn't have any communication with him. Okay, so now let's look at this equation. And this is it's called Creature-Novikov equation. And it's found by Creature and Novikov in 1981. And when they when they try to look for the algebra geometry solution for the KP equation. And the result is any solution. And for this, we call the Creature-Novikov equation can give algebraic geometry solution of the KP equation by some transformation. But maybe in continuous case, and this equation is not as famous as KdV or KP, but it is interesting because it is elliptic. But if you look at the discrete integral systems, and there is a discrete version of Creature-Novikov equation, which is here, and it is found by Adler, it is a young Adler in Russia in 1998. And he found this discrete equation by considering this Backlund transformation of this continuous one. And then he got this Bianchi identity or this superposition formula for the solutions. And he got this equation. But Adler's version is not in this form because his version is written by some elliptical curve of Weierstrass type. But this is later given by Jarmo Hedlund in 2003 and formulated by the coefficients formulated by these Jacobi functions. But anyway, if you look at this continuous limit, and from here, and you can get this. So this is exactly the integrable discretization of the Creature-Novikov equation. And okay, so in discrete systems, and this equation is one of most important equations. It's far different. It's quite different from the continuous ones. So why it is important? I think it's around the year of 2000. There is a property. It's called consistent. No, it's multi-dimensionally consistent. And this property means if you have an equation, for example, this. Maybe I should let me repeat some notations. So here, because it is fully discrete, and then the independent variable are integers n and m, and there is no derivative, and we have this shift. So shift in n direction, we call it tilt, and in m direction is height. So this is usually these discrete notations. So that this is how this equation looks. I mean, if you rewrite it in terms of this n and m. Okay, so this is we call this a quadrilateral equation because it is defined only on 4 points. So for this kind of equations, and if you put the same equation on the 6th face of the cube, so that means you put the same equation on the 6th face of the cube, and if you give this initial value like this and this, and let's call it u and u tilde, u height, and u bar, and then you can calculate this u tilde height from the bottom, and you can calculate this u tilde bar from the left side, and also this height bar from the back side. And then you can also calculate this value, but there is 3 ways to get this value, either from the top or from the right or from the front. So definitely we hope this value is unique. But if it is unique, and then that means the equation is good, it's integrable in some sense. So this is called multi-dimensionally consistent property of that equation. And then this in 2003, Adler, Bobinko, and Suris, they classified such kind of equation with some extra restriction. So the restriction is firstly the linearity, or affine linear. Affine linear means if you look at that equation and it is linear in terms of u, and it is linear in terms of u tilde, and linear in terms of u height, something like that, yeah. And this default symmetry and the Tillerson property. And the Tillerson condition, okay.
Show the previous slide.
Okay.
Decipher for us the equation. So when you multiply u by u tilde, you just multiply them as numbers? Or it was what?
No, it's not number, they are function.
U and u tilde are functions?
Yeah, okay. U is the function of n and m. Look, and this u tilde means n plus 1. So n and m are integers, they are independent variables because this is discrete, there is no continuous independent variables. Yeah.
What is u tilde? Multiplication.
No, u is.
Upstairs, in the first slide.
Yeah. This is the first line, yeah. You mean this one, yeah, okay. U tilde is n plus 1. Yes.
No, but when you multiply the translation, just translation.
The first line, u and tilde, what does it do? The product of u times the tilde.
No, you mean okay. You mean this?
Yes.
The multiply. Yeah, this is multiplication here.
What is p? P is a function of.
No. P is okay. P is the space. We call the P the spacing parameter. Sorry, I should explain more about these notations. So okay. So P is the spacing parameter. Now you have these continuous ones. You have interval, and then you can discretize by this n times p, and then this point you can call this is x0 plus np, and then now you have this some map from x to n, and x plus this p to n plus 1, this kind of thing here.
And what is capital P?
No, capital P. Okay, so the small p and the capital P are they together they are points of this curve.
What is
Okay.
R small?
No, R. Okay, R small is also also on this curve, but they are related, but R is related to P and Q. It's some kind of addition. I think it's maybe you can say you can say 3 points, but you can also say 2 points because this R is in some sense yes, yes. Okay. So now let's go. Okay. So in 2003, and other Bobinko and Suris, and they classified all of these quadrilateral equations, which are affine linear and default symmetry, and this tetrahedron property. Tetrahedron property means if you calculate this the value of this point, and you found this it's only related to your tilde, your head, and your bar, it's independent of you. So these 4 points is just some tetrahedron. And the result is they found only 9 equations on their list. And the equation on the top is nothing but this discrete Kracher-Novikov equation. This one, they call it Q4.
So excuse me, so PQ are now arbitrary?
Yeah, not the P and Q are arbitrary. No, R is related with P and Q in that Q4 equation here.
So there is a elliptic curve.
Yes. So this equation is very quite interesting, but it's also difficult.
And in other P and Q are...
No, in other there is no R since. Yeah, so that is the equation on the top, and so you can take some degeneration of.
So behind Q4 there is an elliptic curve.
Yes. So there are now 9 equations, and most of them are known because, for example, this one, the first one is they call Q4, and I don't know why they use this Q and A and H. And but Q4 is a discrete Kracher-Novikov equation. And this Q1, if delta is also parameter, you can take delta to be arbitrary. For example, if you take delta is 0, and then this is the cross-ratio equation, it is related to the discrete Cauchy-Riemann condition. And this H1 is discrete potential KdV. And this H3, if delta is 0, H3 is modified KdV. So this is the classification, the result of classification by other Bobinko and Suris. But anyways, the discrete Kracher-Novikov equation is the most interesting and most difficult and the most important equation in this list. And all the lists are quadrilateral equations, or you can say this is the 2-dimensional discrete equations. And if you look at the solution of this discrete Kracher-Novikov equation is too hard. I think that so far the best result is from this paper, but they got solution, but this is far from the fully understanding of this equation. So if you are interested, and you can work on this equation. And okay, so it's some more connection with Kracher, and this 2 persons from Leeds, and they found they want to get this maybe they want to construct or they want to formulate this discrete Kracher-Novikov equation in some direct way, and unfortunately they didn't get the Q4 equation, that didn't get the discrete Kracher-Novikov equation. But fortunately, they got all of the solutions for other equations except this top equation. So this is another result. Okay. This is another result. And okay, now they call that solution is elliptic soliton. And actually, it is an eager creature who suggested using this words, elliptic soliton, for this kind of solution, so that it is you can keep the different from the algebraic geometric solution. So what is the elliptic soliton? Elliptic soliton is the soliton solution is characterized by Lamé function. And if you look at this, for example, the KdV equation, and we have this usual one soliton solution, and this exponential function, we call this plane wave factor. And if you replace this plane wave factor by Lamé function, and you will got elliptic one soliton solutions. And if you look at the picture, and it looks like this. This P function is the background. So usually we make some shape so that we can get real value solutions. So the P function is a background, and this is the one soliton solution. This is the one soliton solution, one soliton. And this kind of solution was found for N soliton, was found very earlier in 1974 by the Kuznetsov and Sasha Mikhailov. And they got this N soliton solution, but only for the KdV equations, not for other equations. I don't know why, but after many years, and Nijhoff and Atkinson, they got same type of equations, but in discrete case for the ABS equations except Q4. Okay. So now we come to the outline of this talk. So we will focus on this kind of elliptic soliton, and mainly we will introduce this tau function and the vortex operator, and for this type of solitons, and the example is continuous KdV equations, but we will move to the discrete case also, because if you use the mirror coordinates, and then you can get the discrete result. And we will also see the direct linearization results for this type of solutions, and also this Marchenko equation, and finally some problems. So now let's look at the KdV equation. And for the KdV equation, we have last pair. And if you, okay, anyway, but we know, yes, this U is minus 2 px, and it is a solution of the KdV equation. And then for this Schrödinger spectral problem, and if you take U to be some elliptic function, then we have Lamé equation, and the solution is called Lamé function. So now this is the Lamé function. Okay, so that means we can replace this exponential function by Lamé function, and then we can get this elliptic soliton. I should explain some notation very shortly. So we use this W1 and W2 and to be this half period for the elliptic functions, and here this P and theta and sigma are three Weierstrass functions, and also this P and P prime and satisfy this curl, this elliptic curl, and the G2 and the G3 are invariants. And we will use some identities, but don't worry about that. And this talk, and we don't have any technical thing. But please try to remember this eta u of z. It is a summation of 3 theta functions, and this chi u and z is the summation of 4 theta functions. And there are also some other formulas, but you don't need to remember them. Okay, So now let's recall some result about this bilinear. Here I introduce his bilinear operator, and there is two ways usually, but two ways to define it, but two ways are equivalent. You can expand. For example, from here you can expand it in terms of epsilon and kappa, and then you can compare the coefficients of both sides, and then you can get the formula of this. So this is the definition for Hirsch's bilinear operator, and there are two important and simple identities. The one is if two functions are simple, this exponential linear function. Exponential linear function means the power is linear of x and t, and then the result is very simple. So that means if eta 1 and eta 2 are same, or if a1 and a2 are same, and this will be 0. And the second property is called gauge property. If you multiply this f and g by same exponential linear function, and this function, this exponential function can be picked up out. So this is called gauge property. And and this is an example of bilinear form of the KdV equation. So what about this? What happens if we replace this Euler exponential function by Lamé-type plane wave factor? So for example, if we use this, and let's first calculate the derivative. But since this coefficient is x dependent, and then we should have this. We will have this. So remember, this chi delta epsilon is defined like it's a summation of full zeta function. But anyway, you can calculate the derivative and the second order and the third order. And we can also calculate this result of Hirsch's bilinear derivative. But so remember, if we put say 2, if we put say 2 exponential linear function here, and it will be 0. It will be 0 because if eta 1 and eta 2 are same, and this will be 0. But in elliptic case, if we use say 2, this Lamé-type function, and it is not 0. So this is quite different point in the elliptic case. And you can go calculate the higher order derivatives, and you can get this general formula. This is one thing different from the Euler exponential function case. But if you want to calculate this higher order Hirsch's derivative, and you can use this formula, but this formula in practice it's not quite good because we need to calculate these things. But anyway, if you use this Bayer polynomial is defined like this, and this y is a function of x, and this y1, y2, and y1 means y is the first order derivative, and y2 is the second order derivative of x. So using this Bayer polynomial, and you can get this some for any function, but not only for the Lamé type. For any function, this rho 1 and rho 2, you can always have these formulas. But if they are Lamé type function, and this GM is defined like this. Okay, so what about this gauge property? We multiply this f and g by Lamé type function, and you will have this. And the second part is not 0 because this is not 0. So if this is 0, and it is the same as the gauge property, so this is called quasi-gauge property. So next is about the tau function and the vertex operator. This vertex operator is introduced by Leposky and Wilson in 1978, and they found this like as a representation for A11. And later is Date, Kashiwala, and Miwa, they introduced the time, and they got this, and they show, okay, this is some transformation from this n-soliton solution of tau function to n+1 soliton solution. So this vortex operator is some kind of transformation in the tau function space. And so this is a well-known result, but this is, of course, this is a quite important result in the history of integral systems, because by vortex operator, and we can contact us on one side to algebra and on the other side to integral systems. And in their paper, and they have 3 examples, and the vortex operator are related to A11 for the KdV and the GL infinity to Kp, and also this O infinity for BKP. Okay, so this is the introduction, some introduction. And now let's look at this vortex operator for elliptic soliton solution for tau function. So we start from the KdV, and we have this, now this, we start from this potential form of the KdV equation, and this is the transformation. And in this transformation, we need to use this G2. And then the bilinear form is here. If you replace this tau by this tau prime is tau multiplied by sigma x, and we have this. So this, if G2 is 0, it is the same as back to the normal case, normal soliton case of the Hilbert bilinear form. And then we can use this, and we calculate these soliton solutions. So the simple case is this. You just substitute and then verify it is the solution of this. But for the two soliton case, usually for the two soliton case, and we suppose the tau2 is like this form, and then this term, this nonlinear term, should be the multiplication of these two terms plus some some phase factor. But this is different from the usual soliton case. And if you look at this F2, it is not simply product of these two terms. And so this is not product of this and this. But A12 is quite quite good form. So, and one more interesting thing is we can look at this dispersion relation. Dispersion relation, if you expand this theta and p function at 0, and you have this is something like 1/2, and this is 1/1 k, and this is 1 k cube. So this is in some sense, our asymptotically is corresponding to this k plus kx plus k cube t. And it's difficult to go further to have 3 soliton solutions by direct calculation. And then we move to the Wronski. So, if we use Wronski, and then if the component of this Wronski satisfy this differential equation system, and then it's quite easy to prove this tau satisfy that bilinear equation. And we can have a solution because we can even have this general solution because it's a linear system, and the solution is this. And we have this phi j plus and phi j minus. So, and this aj1, aj plus, and aj minus are arbitrary constant. And then we will convert this Wronski into Hilbert's form, into this form, because once we have this Hilbert's form, and then we will look at this vortex operator. So it turns out that we need to introduce a shift. Here the theory is not a discrete variable; it's just a shift for the x by this. And we introduce this tau tilde, we introduce this g tilde, and g is defined like this. And G is actually Wronski if you just use this part. If you take this aj plus 0, and aj minus is minus 1 to the j. And then that Wronski will give you this function g. And first you make shift, and then this tau tilde divided by g tilde, and you have f, and this f is still the solution of the same binary equation. But if you in the normal soliton case, we don't need to make any tilde shift. But this f, and it has this form. This is the Hirt's form. And once we have this Hirt's form, and then we can introduce this vortex operator. This vortex operator is different from the classical soliton case. In the classical soliton case, and we have this operator form, and this operator form is the same as actually the same as the Euro-soliton case. But here, this is the dispersion relation part. It's different. We need to Lamé type function, and we need to using the derivative of theta function to define this. But this is different from this Euro-soliton case. And then you can prove that this is a transformation between this tau function between different soliton solutions. But here is one more problem. One problem is we want to look at this algebra corresponding to this vortex operator, but so far no result. For the Euro-soliton case, it is A11 for the KD way, but we tried that for a long time. So far we don't know what is the algebra corresponding to this vortex operator. And once we have vortex operator, and then we can go to find this bilinear identity, and we use this vortex operator, and we have this tau function. But this operator is some kind of square root of that vortex operator. We have 1/2 here, and this vortex operator is doubly periodic. No, not vortex. Okay, this integration and these two functions, if you look at Q, and it is doubly periodic with respect to Q, and then that means we can take this counter to be this boundary of this fundamental domain, and then the integration will be 0. So this is the identity. It is bilinear, and then we substitute this tau because this tau is already known. Tau is here, and we substitute this tau into here, and then you can count this residue, and you will find that all of the residues are this ki and minus ki. They are simple poles, and then you calculate the residue, and you will find they can be cancelled, and then finally, and this integral will convert it to this to calculate this residue at 0, and then we can calculate that. We can calculate this residue, and of course we need to introduce this Hirt's bilinear operator, and this is the Euro way. We can introduce this x and y. I mean, the t bar is x plus, and the t prime is x minus, and then in this way we can introduce this d operator. But up to here, and if you expand this function, or expand these two functions in terms of Q, and then you can calculate the residue, and then you can get the binary equation. But for this, it's impossible, because you can expand that, but you cannot get explicit formula for these coefficients. So it's difficult. It looks something like it's quite hard to calculate this residue. But fortunately, we found a formula, and to get that residue, and then we can get this bilinear equation. I won't to explain any technical things, and I just show some examples. So these are some bilinear equations in the KDV hierarchy. If you take this G2, G3 to be 0, and then you come back to the KDV hierarchy, the bilinear hierarchy. So this is for the KDV. And for the KP, it's quite similar. So we have this potential KP equation transformation in bilinear form, and then this top function in Wronski, and this top function in Hilbert form, and then this vortex operator. And in each vortex operator, and we have two spectral parameters, K and L. So this is for the result of the KP. And also, we have the bilinear identity for the KP and also some bilinear equations. So usually we have, once you have the result of the KP, and we can consider this reduction. And for example, reduction to reduce to the KDV and reduce to the Booth-Nash. But if you want to get a solution for the Booth-Nash, and we need to consider some, we call that a cube root of our elliptic cube root of unity. So we can define this nth unity, elliptic nth unity of unit, because now we have p function. This is the derivative, and this they can factorize like this, and this omega j delta we call that elliptic nth root of unity. And they have some nice property, but okay. So when n is 2, and we have used it to define this Lamé type plane wave factor for the discrete KDV, and when n is 3, and we have this something Lamé type plane wave factor for the Booth-Nash. So maybe I can explain something on how this plane wave factor defined using this plane relation curve. So if n is 2, this is quite simple. If we have p plus k and p minus k, because this root is just the k plus k and minus k, and this is the way to define the discrete plane wave factor. But if n is 3 and we have cube root, and we can have this plane wave factor for discrete Booth-Nash. So in elliptical case, and we can do that in the same way. But anyway, it's from here, and we can get, or we can study the Lamé type solution, our elliptic soliton for the Booth-Nash also. But we can also use that to consider the reduction. And for the reduction from the KP to the KDV, it's quite easy. For the whole hierarchy, it is okay. But just you take this Li is minus Ki. But if you want to get the solution for the hierarchy of the Booth-Nash, it's almost no way. So why? Because, okay, so once you have, for example, once you have a cube root, and the cube root is automatically the 6th root of unity. But in the elliptic case, if you have a cube root, the cube root means this is 0. And okay, but if you look at the 6th root, and this should be 0. But this can be written in this form. So if it is a cube root, this is 0. But we need this 0, so here, that means either G2 is 0 or this is 0. So this is 0 means it is a square root, but it is not, of course, it's not a square root. So it must, G2 is 0. If you don't want to take G2 to be 0, then that means the cube root is not the 6th root in the elliptic case. So that means you cannot get a solution for the whole Booth-Nash hierarchy by reduction from the result of the KP. This is the elliptic case, but in the Euro-Soliton case, it is true. So this is a problem. Okay, so, But of course, we can look at the degeneration by period. If the degeneration means the discriminant is 0, and so the one result is this is if you take G2, G3 like this, and you have this discriminant 0 discriminant, and then you can get this trigonometric case and also this rational case. So this is not difficult. It's just show some formulas. And this is the trigonometric, and this is the rational case. And also for the discrete, for the fully discrete, this is H1. Remember, this is the bottom equation in of the Adler-Babingo series list. And so this equation can be binarized like this. If you want to get this elliptic soliton, and we need to some special settings. For example, this disk C is under the plus m epsilon, and this h is just a parameter. And but anyway, we have a bilinear form. We have this causality because it is a discrete Wronski, and we have this also this Hilbert form. But if you look at this vertex operator, we can use some trick by Miwa. We can expand this, or we can rewrite this discrete exponential function into continuous form. I mean, this row can be written in this form. But if you look at this form, this is nothing but the function that we used for the continuous KdV. So that means if you use the Miwa variable, and you don't need to consider, you can use the same vertex operator for the discrete case. So that means for the KdV, no matter it's discrete and continuous, and they have the same vertex operator. And also for the Kp. So this is the first part. And the second part, okay, shoot fast. The second part is about, the third part, okay. Because the first part is interaction, the second part is bilinear, and this is the third part is about the direct linearization approach. So what is a direct linearization approach? And in 1981, and Foucault and Avlois, and they introduced this integral equation. And so this integral equation, the unknown function is phi. And if if you have phi, and using phi, they can define u, and then they can prove this u is a solution of the KdV equation. And how to prove that? And actually, is from this phi, and they can get another function, and that eigenfunction of the Lux pair of the KdV equation, and then they can verify this u and that eigenfunction satisfy the Lux pair of the KdV equation, and then this is the solution of the KdV. So that means, but anyway, in their approach, and they need Lux pair. And almost the same time, just 1 year later and 2 years later, also by Dutch group, it's by this Nijhoff, Quisberg, and Kuiper, and they have I call this direct linearization plus. This is the simple. This is the quite in practice is quite good. So they introduce I call this finite infinite matrix, and they introduce this infinite column vector by this integral, and this omega is kernel, some Cauchy kernel, and this is also this infinite column vector. And then they by this U they can define this capital U. This capital U is infinite side matrix, and then they can find some relation between the components of this matrix, and then some relation can be closed, and then closed form can be considered as integral systems. And then this integral system, then you can have Lux pair. And the how to get the Lux pair, and actually this UK, you can find later. You can find they can satisfy some linear relation, and this linear relation will be used to define Lux pair. So this is the Dutch way, and this is quite universal, because it is you just replace this plane wave factor. For discrete, you can use this, and for continuous one, you can this. You can same structure, and you can get this KP discrete or continuous KP. So, and then what about the elliptic? So for the elliptic type solitone solutions, and we have this integral equation. So you can make a comparison here, and we have rho k. This rho k is the Euro solitone. This is a Euro solitone plane wave factor, and here we have this omega, this Cauchy kernel. And for the elliptic case, we have several different things. And here this rho k is we call this elliptic version, elliptic plane wave factor. And this Cauchy kernel is not Cauchy kernel, it's the elliptic Cauchy kernel. And here we also need this. But anyway, this scheme works. And we can get this KP with the elliptic solutions. And also you can get this modified KP, you can get Schwarz KP, and you can also get the Boussinesq if you use this elliptic cube root of unity. And this is the Boussinesq. This is some simple form of Boussinesq. Okay, so we also hope to look at this Marchenko equation. In the Fokas and Abeloy's paper, and they show how to get Marchenko equation and from their own approach. So from that, their integral equation from this phi, and they introduce psi. So this psi is the eigenfunction of Laxpai of the KdV. And they use this psi, and they can define this k and f, but anyway, they should show this integration convergent in the plus infinity. But they do that. They can do. Of course, they can do that. They did that, and then this is the Marchenko equation. So what about the Marchenko equation for the elliptic case? But first, we need to deform this Fokas and Abeloy's integral equation. So we have this. We have this. We call this elliptic direct linearization scheme for the KP equation. This is the integral equation, and we have this we have this. Where is my rho k? Sorry. Okay, here. This is my rho k, and this is psi, and we have this. This is the KP, and we have this integral and equation, and we have this solution expression, and we can prove. You can prove that, and this U and this phi satisfy the Laxpai of the KP, and then that is the will give the solution of the KP equation. And then from this, and we can make some trick, because this is the well-known trick, is to get the real value of the function, elliptic functions. You can take this one period is real, and another one is a pure imaginary, and then you can make some analysis, and then by analysis we need to choose this some kind of a domain for this R and M prime, and then you can get some real value functions, and also you can prove this integral can be convergent at plus infinity, and then it's okay, and then you can get this. We can introduce this k and f, and we can get this Marchenko equation for the KP. But of course, and the reduction is available, and you can we can get Marchenko equation for the KdV and also Boussinesq. So okay, these are the third part, and this is the solution, the line soliton solution for the KP. And you can also have these two soliton solutions. So the final part is some problem. So the first problem is, like I mentioned, is a discrete creature of Novikov equation, and this is so far it is too difficult. Probably maybe after 5 years, and I can have some progress, and then I can report. But I hope is maybe you are also interested in this equation, and you can have some new result about that. And the second problem is the vortex operator for the elliptic soliton solutions, because so far we don't have any algebra correspondence with this kind of vortex operator. Without algebra structure, and we cannot go further. So this is also important thing, one thing. And the third thing is, let's just take the Busnes as an example. Because the cube root, elliptic cube root, is not the elliptic sixth root. So that means you will have a problem if you, by reduction, to consider the solution of the whole Busnes hierarchy. So how to get the elliptic soliton for the whole Busnes hierarchy? Or is there any other way and to define this elliptic nth root? So this is the third question. And the last one is, we hope to formulate KP in Satos approach. And somebody did that, is by this Saburo Kake, and he had a recent paper. And he found this V0. And this is quite similar to the Euro-soliton case in the Satos approach. And the coefficients for this V0 operator is this, and he found this, and he can define this this pseudo differential operator, and like this. So that means, and this will be the solution of the KP. But this looks everything is good, but if you calculate the square, and we hope to have some truncation, from here, so that we can get this Schrödinger spectral problem or Schrödinger spectral operator. But this truncation does not work, because if you make truncation, that means this term should be 0. That means G2 should be 0, and all others should be 0. But it's impossible. So that means that this Kakas, I think there is another way to formulate this Satos approach. So this is my last problem to show that. I think I stop here.
Okay, many thanks. I needed a bit time to turn off the mic. Are there any questions or comments?
So what does this mean? This means like you don't have a, so you can construct like a directly solution of the KdV.
No.
I mean, like you don't have like a Galvan-Dickey hierarchy. Just
But so the simple case in the Galvan-Dickey hierarchy is a KdV.
yes, yeah.
But if you want to get KdV, and then that means you can take by some restriction or constraint, and this part can be 0. But now you can look at this cannot be 0. So G2 cannot be 0, and this cannot be 0. So that means at least in this kind of formulation, and the reduction is not okay.
That's only because your L0 is
Very
very restrictive, right? Because you
no, this is for the KP. L0 is for the KP.
Yes.
The pseudo just the pseudo differential operator for the KP. But I think he already take this the P function is like a background solution for the KP.
Mm-hmm. But this is not the only choice, right? of this L0?
I think it's not only choice.
Because
There
other
should be some
coefficient-
good things can be truncated.
Right, because other coefficients of partial inverse, like partial negative to the i's, it seems like other coefficients are already determined in this case. But in general, it shouldn't be.
No.
Okay, thank you.
But for the KP, and it works. You can get this Wronski solution for the KP.
Are there further comments? Yes.
Not about black spare. Yeah. Do you have any ideas how to construct new formulation for KP? I'm asking about this slide. Yeah. Do you have any ideas how to construct new formulation for KP? Yeah.
So to be honest, that we also try to look for this kind of structure, but so far we don't have good results. Yes, so this is a result by Kake, but like here, and the truncation does not work. So there must be some other formulation for the KP.
Have you discussed with Kake about this issue?
No.
Okay.
No.
And I'm wondering, is there any semi-discrete analog of your elliptic solution?
Yeah. Yes. Yeah, there are. Yeah.
You can formulate the elliptic solution for semi-discrete hierarchy by the similar approach.
Yes, there are, because once you have fully discrete, and then you can have some semi-discrete. Yeah.
Okay, any further questions? If that's not the case, let's thank the speaker again.
Okay.
No break, right, Anton?
No break.
Just quick switch.
Huh? Okay.
We have 3 minutes break. It was just announced.
Huh? What was just announced?
3 minutes of break.
3-minute break. Okay. Take people need. Okay. Okay. Right now, as an organizer and not as a speaker, since I haven't been introduced yet, quick notice to participants. If you chose cash reimbursement and your bank cannot receive cash reimbursement, come talk to me, because the deadline for cash reimbursement is long gone. Okay? Now you can introduce.
What do you mean your bank can't receive cash
You cannot transfer from here to Russian banks.
They're all.
А? No, cash reimbursement. Из-под стола. А? Но никто же не услышал. Okay.
Okay, welcome back. The last talk of today before the exercises will be by Anton Jamai. Correct?
Yeah.
Oh, I learned how to pronounce your name. And the title is Geometry and Symmetry of Pavlov Equations.
Okay, well, thank you very much. And thank you for still being here. So I realize that everybody are getting tired. So I decided that my talk will be very, very elementary. And in that sense, it's not aimed at the people in the front row, but rather to the thinning back rows. Okay? No, we don't have time, right? No offense was intended. Okay, so, but again, I'll try, rather than focusing on actual equations and formulas, I'll try to explain a little bit of the general picture of the theory of Paine-Levé equations from the geometric point of view. Okay? So, that's essentially the title of my talk, Paine-Levé equations, geometry, and symmetry. And the plan of the talk is the following. So first, I will say a few words about Paine-Levé equations. Like, what are they? And why are people interested in them? Second, I will explain where the geometry appears in the theory of Paine-Levé equations. And this geometry is known as Okamoto space of initial conditions. Okay? Which, despite the way it sounds, is actually a family of certain rational surfaces, rational algebraic surfaces, so-called generalized Alfvén surfaces. Okay, so we start with some equation. From that equation, we can get a geometric object. And then we can look at the symmetries of this geometric object. And so symmetry comes from geometry. And symmetry here are something called Cremona isometries. So these Cremona isometries are associated with the surfaces here, and the group structure of Cremona isometries in this case would be some Weyl group associated to some root system or some Dynkin diagram, and this Weyl group would be affine and also extended. Okay, and the nice thing about this is by looking at geometry, it's clear how to compute these symmetries. And what the symmetries do, they create symmetries of your equations. They are known as Backlund transformations. So Backlund transformations, these are symmetries of your equations. Okay? And because we have an affine Weyl group, so this is like step 3, and I think I'm done with my title, and I'm very afraid that that's about where I would start running out of time. However, if there is a little bit of time left, because while groups are affine, from here you have translations. Translations in affine while groups. And you can think about such translations as defining a discrete dynamical system. You just go by some fixed vector in some affine space, and associated to this fixed vector is actually a nonlinear equation, and this nonlinear equation became known as discrete Painlevé equation. And the reason such equations are known as discrete Painlevé equations is because you can do a continuous limit, go full circle, and get. But what usually happens is you start with some Painlevé equation, for example, Painlevé 6, find its associated geometric object, look at its symmetries. In Painlevé 6, it will be affine D4. Look at translations and take continuous limit, you will end up with a Painlevé 5 equation. So this would be like a discrete Painlevé 5. Okay? So my goal is to give you some idea of how this machinery works. Yes, there is something called Q Painlevé 6. And that's not something that I will be talking about. Okay? I apologize if I'll be shutting questions down a little bit, because there's a lot of stuff here. You open the lid a little bit, and there's a whole Pandora box of interesting stuff. If you want to sacrifice a coffee break, let me know, and then. Huh? Affine D4. I don't understand. Huh? Yeah, you'll see what it means. Okay, so as I said, my talk is for the tired people at the back, essentially. That's why, to explain what a Painlevé equation is, I will start with something very simple, like y prime is equal to y, and I apologize for doing that. Now, why is this equation important? Because this is an example where you start with an ordinary differential equation, and you get an interesting or special function as a solution. In this particular case, of course, the function that you get is one of, if not the most important functions, right, the exponential function. And the way to think about that is you allow t actually to be a complex variable. You allow complex time. And then you can think about this as a power series. And that follows directly from your differential equation using the method of Frobenius. And all the properties of the exponential function, like the fact that it takes addition into multiplication, you can get directly using the language of differential equations. Okay? So ordinary differential equations is a good source of interesting new functions. Of course, this is something very, very simple. If you try to do something a little bit more interesting, you can try, and I know I should remember this, but I don't. You can look at the following equation, E of alpha, beta, gamma. Okay? So and this equation is known as a Gauss hypergeometric equation. Huh? Can I read it? Yeah. E alpha, beta, gamma. So it's a second derivative of some function w with respect to time, and coefficient gamma minus alpha plus beta plus 1 multiplied by t divided by t1 minus t dw dt, and then minus alpha beta t1 minus tw equal to 0. So this is known as a Gauss hypergeometric equation. And this is one of the sort of prototypical examples of differential equations that gives a source to many special functions for degenerations. If you think about time t, actually not even a complex parameter, but living on the Riemann sphere, this is an equation that has three singular points, or three regular singular points, one at 0, the other one at 1, and the other at infinity, okay? And the reason you have singular points is because you have singularities in the coefficient. When t is 0 or 1, this coefficient is equal to, the denominator here becomes 0, or if you clear it off, the coefficient at the highest derivative disappears. So you see that we have singularities. Okay, and the singularities can occur in two different places. You can think about singularities occurring. Oh, nice. You can have singularities occurring in equations, and you can have singularities occurring for functions. Okay, so equation or solution. Okay. And then the question is, how are the two connected? If you have a singularity of an equation and a singularity of the solution, well, it turns out that you can sort of say something like this for linear ordinary differential equations. So what I'm saying is the following, that if your equation has coefficients that stop being analytic, for example, at a certain point, you can have solutions that become singular at that point, but not necessarily. You may have solutions that are not singular. For example, for the Gauss hypergeometric equation, you have something called the Riemann scheme. And these parameters, alpha, beta, and gamma, that we saw there, I think, no. Okay, tell you that you have a fundamental system of solutions, one of which is regular, and the other may have power behavior of 2 minus gamma at this singular point and behavior at infinity. So here you have your alpha, beta, and gamma as complex parameters. So in the linear case, the control over singularities of solutions is completely provided by the equation. However, if you go from linear equations to nonlinear equations, a whole lot of properties disappear and life becomes very different. On the other hand, if you are using differential equations to describe special functions, it makes sense to try to construct nonlinear special functions from nonlinear differential equations. Okay? But then there is a problem. And so let's take equation that is as simple as the very first one that I wrote. So dw dt, but instead of y or w, I'll take w squared. Okay? This is a simple first order separable equation, for example. You solve it by rewriting in differential form and integrating. Okay? And how do you find this constant of integration? Well, you need to have an initial condition provided. So let me add to my equation an initial value problem that w at t naught is w naught. Then it's easy to evaluate this. This can be written as t minus t naught minus 1 over w naught. And then you can solve for w of t. This would be something like w naught 1 minus w naught t minus t naught, or something like this. Okay? Up to small typos. So what do you see? First of all, you see that this solution has a pole, because denominator can vanish. Second, you see that the location of a pole, so This is a pole at time t, and you can see it from here. So what is my t is 1 over w naught plus t naught, I think, something like this. Okay, so such singularities are called movable. So this is a movable singularity. So movable singular point. And the word movable here means that it depends on initial conditions. Okay? So now, it's not the equation that controls your singularity structure. It's the initial value problem that controls the singularity structure. And a pole is something that we can handle. But if you look at something like this, w squared dw dt, let's say 3, is equal to 1, and let's say w of 0 is w naught, because of course the initial value of time doesn't matter. Here you will get something like w cube is t plus w naught cube, and you solve. You get the branching point phenomena. So now you have a singular point at minus w naught cube, and then another singular point at infinity, and you need to do a branch cut. And here, the location of the branch cut starts depending on initial value problem. And that really is an issue, because if you want to construct the Riemann surface of this solution, you really need to introduce moduli on these Riemann surfaces. So, and what that means is what we have here is actually still good, but what we have here is really not good. Okay, and this is not a very mathematical way to say it, but a mathematical way to say it is that here you have Paine-Levé property, and here you don't. Okay, so Paine-Levé property is, of course, goes back to Paul Paine-Levé. And he was interested in finding differential equations and classifying differential equations whose general solution has no movable points like branch points. For simplicity, we can say that Paine-Levé property is general solution or movable singularities of general solution are poles. Okay? So that's Paine-Levé property. And Paine-Levé, together with his students, but especially Gambier. No. Paine-Levé property is general. I think I'm thinking in terms of, okay, let me think about it. You caught me off guard a little. Definitely for second order, yeah. Okay, here, we'll talk. I always work in second order, so I don't think beyond, but I think it's the same for third order equations and higher order equations. The Paine-Levé property is still the same. Okay. Oh. Anyway, so there is a classification due to Paine-Levé and Gambier, and then independently Fuchs, of special second-order equations that satisfy this property. So equations are of the form like this, and here you have some rational expression in W and T. So you have P1, and I apologize, I have horrible memory, so I cannot remember equations at all, even as basic as Paine-Levé 1. This is embarrassing, but it is what it is. So you have Penlever 1, have Penlever 2, d2w dt square is And what's interesting here, you see that there is a parameter alpha appearing, and you have Penlever 3, and I don't want to write it. And then you have Penlever 4, and that one I will write. It's a bit more complicated. Okay, and again, you see here that you have parameters now alpha and beta appearing. Okay, and there are two more. There is Penlever 5 and Penlever 6, and if people are feeling that they should add two more to Penlever 5, don't. I know about them. Okay, these equations, they come in a cascade. So you have more parameters in Penlever 6. You try to degenerate parameters. You can degenerate to Penlever 5, and you can degenerate to Penlever 4 and Penlever 3. You can in turn degenerate this to Penlever 2, and all the way to Penlever 1. So that's one thing. And another thing is you have special values of parameters alpha and beta that give you special solutions. Okay? So for example, here you can get this hypergeometric functions as a solution of Penlever 6, or solutions of Penlever 6 expressible in terms of hypergeometric functions for certain values of parameters. Yeah. Well, you have different properties. You have different symmetries. You have different type of special solutions. So it's not that if you know, well, first of all, I think it's hard to know everything here. It's much easier to know more here than there, right? So you have that. And if I can get a bottle of water that I didn't think about, I would appreciate it. No. Okay. So we have special solutions. So here, so here we have Kummer, here we have Bessel, yeah, here we have Bessel, here we have Airy, etc., Hermite. Again, it's important that there's some values of parameters that are special. Okay. But in general, it is very difficult to keep any track of solutions of Penlever equations. The method of Frobenius doesn't work. How do you represent a solution? How do you study its properties? And there are a large number of techniques. For example, you can use something known as a Ribon-Hilbert analysis. But one of the approaches on trying to describe solutions is due to Kazuo Okamoto. And now I am moving to the second part of my talk. Who decided to understand the solutions or parameterize the solutions by initial conditions, which is the most natural thing, right? Try to, by Cauchy theorem, your initial condition uniquely determines your solution in some time interval. But for that, it's better. So for example, if you start with P4, it's better to rewrite that as a Hamiltonian system, H4. And there is a little bit of a catch here. So Okamoto Hamiltonian for H4, and I will use here variables f, g, and t. That would be 2f g square minus f square plus tf plus kappa naught g plus theta infinity f. Okay? Now, here, notice that even though I call this function as Hamiltonian, it is something known as a time-dependent Hamiltonian function, so it is not a constant of motion. It's evolving with time, but nevertheless, you can still take the symplectic form, and let's take the standard symplectic form dg df, and generate your equation. Then you have f dot is hg, and g dot is minus hf, and okay, I should be able to do that. 4fg, right, minus f squared plus, I'm just following the advice of Ned to do it in public, right? So here, what do we have? Minus 2g squared plus 2fg plus tg minus theta infinity, something like this. So you get a Hamiltonian system, but notice that it's not that f a coordinate and g is a momentum. It's a little bit more complicated than that. Okay? And turns out that this system, if you rewrite it for just f of t, let me call this Pandeva4 denoted by star. So here, this is star for w of t is f of t. And notice that here I used parameters alpha and beta, and these are standard parameters for this standard form of Painlevé-4. And here I used kappa naught and theta infinity. And they're related, of course. So alpha is 1 plus 2 theta infinity minus kappa naught, and beta is minus kappa naught square. But of course, I could have skipped that. But the reason I'm showing this is when you have equations coming from a particular applied problem, your parameters are related to parameters of a problem, and you need to be able to match them with the standard parameters. Sometimes it can be difficult, and geometry actually tells you how to do that. But, okay, anyway, so you can show that this system is equivalent to Painlevé-4. Then you start thinking about the space of initial conditions. Everything is complex, so this line is actually a complex plane in the colloquial sense. This plane is an actual complex plane, C2. This is a plane of my variables f and g. And then if I pick up a point here, I will have a solution. Okay? And remember the type of singularities we're allowing for Painlevé equations. We're allowing poles. So what can happen is this equation can go away to, this solution can go away to infinity at some value of time. But on the other hand, of course, some other solution can go away to infinity for our value of time. So we want to try to account for these infinities. And what we need to do, we need to projectivize this C2. And there are two ways to do it. You can projectivize C2 to P2, or you can think about C2 as C1 cross C1 and projectivize it to P1 cross P1. And this is what I would usually do. It almost doesn't matter. For Painlevé-1, you need to do this, but Painlevé-1 is also not the one I'm interested in. So if you know a little bit of algebraic geometry, you know that these two are different, but they are what is called birationally equivalent. Okay? And it's a very nice thing that now we got us a compact complex surface, two-dimensional complex manifold or two-dimensional complex algebraic variety, and compact. So you immediately can talk about things like homology, cohomology, Poincare duality, etc. So in this case, if you look at H2 of P1 cross P1 Z, it's the same by Poincare duality as this. It's the same as H1 with the coefficient in the structure shift, so the classifying space is for line bundles. And that's the same as a peak that we saw in Sam's lectures. although in his case it was one-dimensional and here it's two-dimensional, but it's still divisor. It's a set of divisor classes, all irreducible codimension 1 submanifolds, which is really curves on P1 cross P1 modular linear equivalence. It's very easy to understand what this thing is. It is generated by coordinate classes H, F, and H, G, and I want to show it in two different ways. So what is P1? P1 is the same as a sphere, right? So if you want to think about P1 cross P1 topologically, what do you have? Really, you have a product of two spheres. It's very similar to a torus being a product of two circles, and each circle is its generator in homology. So the same thing happens here. One of the spheres is a generator, and that's exactly one of these two coordinate classes. Okay? So, and I need a way to visualize it because I like drawing pictures. So this is how I will visualize it. I will draw it as f equals to 0 line here. So this is my sort of coordinate f. And I add here the point at infinity. So you really should think about it as a Riemann sphere with 0 in the south pole and infinity in the north pole. Okay? And same here. You have g equals to 0. You have g equals to infinity here. Then you have various coordinate charts. For example, here is your little f, little g chart. And for example, over here, there is what I will introduce as a big F, which is 1 over little f, and big G, which is 1 over little g. Okay, so and then there are two more charts, one centered here and one centered here. So we have these four charts. We have this group. This group comes equipped with something called the intersection product. So H f dot hf is hg dot hg is 0, and hf dot hg is 1. And if you use this picture, it's sort of easy to see what's happening. You have a vertical line. This is, for example, f equals to a. You have a horizontal line. This is g equals to b. They intersect at one point, and that's that. Okay? Of course, these are classes, but a class of horizontal lines, you just allow to deform this. And of course, if you deform here, there's still one intersection point. On the other hand, if you want to do this, you take two representatives, and you should use a general position transversality. So you take two representatives where one is a shift of the other, and they do not intersect. Actually, the right way to think about this is you do this shift by pushing the zero section along the normal bundle of the embedding of this line on the projective plane, and you can do that in this case. Okay, so we have that, and then remember our symplectic form. Of course, it's a complex symplectic form, omega dg wedge df, that is completely regular over here, but if you extend it to the all of P1 cross P1, it starts picking up poles. So omega is dg wedge df in this chart, but it becomes d capital G wedge d capital F over F squared G squared in the other chart. So you have poles of order 2. Then what this means is if you take a divisor of omega and take its class, you have poles of order 2 in the first coordinate line and poles of order 2 in the second coordinate line. And of course, this is known as a canonical class. Okay? And in Penlevet theory, this class, or rather its dual, plays an absolutely crucial role. So I will go from here to negative k, which will be, in my case, 2hf plus 2hg. Okay? So this is how geometry appears. However, I am not done because you can have more than one solution going to infinity. So what can happen is, where was that? Over here, right? You have one solution going to infinity here, and you can have another solution going to infinity here. This is, of course, a lousy picture because the dimensions of what we're doing is much higher, but still. So if you think about these two solutions sort of going to infinity together, if you think about this as infinity, you have something like one solution arrives and then the other solution arrives, but they sort of have the different rate of growth, okay? So what you can do is you can separate these solutions according to their rate of growth or sort of naively on the slope on which they enter this point. So you have something like this. So what you do is you take this point and you do the blow up. Okay? So what the blow up does, it introduces an additional direction of slopes. So this would be your slopes. And you lift your curves according to the slope by separating them so that they don't intersect anymore. This is a very standard procedure of resolving singularities in algebraic geometry. So this is blow up at the point P, for example. Okay? So you have this line of slopes, and you can think about it in the following ways. Here, you introduce this additional line, and all possible slopes up to equivalence, that's exactly the projective line, right? So it's a space of lines, equivalence classes of lines for the point. So it's P1, and P1 was S2. So every time you do the blow up, you have to add what is called as exceptional divisor E, okay, that corresponds to this line of slopes, EI, and that will be like an extra sphere because it's your complex P1, and in your peak gets another class epsilon I. That's the class of this sphere EI. And so it's a kind of a surgery where you take a point and you take away a point and you blow a bubble at this point, or you do the sum of P1, I think, with the opposite orientation, maybe not. Okay, anyway, so you have this, and when you do this to your Picard, this EI has this interesting property that it's what is called a -1 curve. So it's a curve of self-intersection -1, and sort of the way to see it is if you think about this picture, it's of course it's a real picture trying to convey some complex geometry, but if you think about this, this is like a Möbius line bundle. So this bundle has no sections, okay? And you can think about this self-intersection as an intersection of a zero section with its deformation, and this one has no deformations. They go to infinity. So that's essentially the first Chorn class of the embedding of a normal bundle of the embedding of E in X, the surface that you get as you blow up. Okay? So you have to adjust your geometry. It's not just projectivizing, it's also separating these possible trajectories that go this way. Okay? So okay. So here is the picture then. We start with C2. We add lines at infinity. Then we look at points where new trajectories can intersect. And if you think about Pannever 4, that was just here, sorry, turns out that this is what you get. You get a point here, and another point here. You get a point here, and another point here, and you get 1, 2, 3, 4 points here. Okay? So what does this mean? It means that here you had this bad point, you did the surgery, you created a bubble at this point, you extend your equation to that bubble, pick up another bad point, and have to do that again and blow another bubble there. So this is the cascade of infinitely close points. Or you can think about sort of curves touching each other, and you need to go further. So you get something like this. So you get points P1, P2, P3, P4, P5, P6, P7, and P8. So here, these are my lines: f equals to 0, f equals to infinity, g equals to 0, infinity, g equals to 0. And actually what I'm doing a little bit of a gauge transformation that I can always arrange for the points to be there. That's sort of what also normalizes the way your system looks like. But then if you think about the point P4, first we need to introduce a coordinates describing it. And to do that, so local coordinates around this point is little f and big G, where big G is 1 over G, little g. So you can introduce the coordinate like little u3, which is just f, and for big G, you write it as little u3, little v3, and this v3 is, of course, just a slope g over f. So that's a slope coordinate. By introducing this line of slopes, you just do this algebraic change of variables, introduce the slope coordinate. You can also call this a coordinate, usually called big V3, and this is big U3, big V3. And these are the two charts. One chart is sort of at the bottom of the P1 and the other at the top of P1. And you can use usually either of these charts to specify. So here, little u3 is kappa naught, and big V3 is equal to 0. That's what this point turns out to be if you do the computation. So what I want to stress is that the coordinates of these points, they depend on the parameters of your equation, on the parameters alpha, beta, or on kappa naught, whatever. Okay, so then what you do is you do the blow-ups at these points, and you keep track of the intersection index of your curve. So let me start with the point P1. So I have this line, and this is a 0 line, and I have this line, this is a 0 line. These are lines of self-intersection 0. I blow up this point, so it now becomes a line. Okay? Let me call this line E1, because that's sort of the sphere or the line of slopes that I created at the point P1. It has the index of -1. Then this line also becomes my index -1, and I will call it HG minus E1, because when you project, this whole thing projects to this line. Just that the preimage of this point is this whole line. So if you want to sort of take what is known as a proper transform, in other words, preimage of this line without the point in algebraic closure, that's the notation that you would use. And here you will have HF minus E1. So that's blowing up that point in the corner. Now, there is one more point appearing. So somewhere here will be a point P2. So if we blow it up, we will create here a line E2, sorry. And this line, now by the same token, I want to write it as E1 minus E2, but I will also change the color here. Write it as E1 minus E2, because this now is a -2 curve. Okay? You can check it just by computing the intersection index. So you do it over there as well. So here you will have E5 minus E6. This line would actually be HF minus E1 minus E5, E6 minus E7, E7 minus E8, and here you will have E8. Here you will have HG minus E3 minus E5, E3 minus E4. This one would be HF minus E3, and here you will have E4. You get a diagram like this, where I color-coded red curves are -1 curves, and blue curves are -2 curves, okay? And that's where this Dynkin, that's where the affine Dynkin diagrams start showing up. Let's look at the configuration of these blue curves. If you draw them, you see that you have a chain. Let's start here. You have this curve, then this curve, then this curve, then this curve, then this curve. So this would be, let me call them D1, D2, D3, D4, D5. So this is my D1, D2, D3, D4, D5, and I will call this D6, and I will call this D0. And, oh wait, D3, D4. No, D6, D0. I'll leave it like this. Doesn't matter. Okay, so if you look at this diagram, many of you will recognize that this is what is known as affine Dynkin diagram A6. Okay, and this affine Dynkin diagram comes with a generalized Cartan matrix, and the generalized Cartan matrix here, it's up to a sign because we're thinking about self-intersection. So this is index -2, and then D0 doesn't intersect with 1, 2, 3, 4, 5, intersects with 6. Then D1 doesn't intersect with D0, intersects with itself, and so on. You can fill in this diagram. And this matrix is degenerate. It has a null vector or vacuum vector. That's exactly where the affine part of the affine Dynkin diagram comes from. And if you, so there is a vector here that you multiply to get 0. Turns out that you can see the coordinates of this vector from the diagram quite easily. There will be something like this. And that whole thing, if I call it delta, turns out that this is exactly the anti-canonical divisor class. And what we have here is decomposition of anti-canonical divisor class and this decomposition corresponds to geometry because each of these summons here is the equivalence class of some -2 curve that we got. Okay? So I know I've been talking a lot and probably a bit fast. So, let me slow down and try to make the main point clear. When you construct a space of initial conditions, you need to add the infinities to allow for poles. When you add infinities, you get points where some trajectories can merge. You separate them using blow-up. You create a complicated algebraic surface, and that's the encoding of the surface that you created. Okay? So this surface is known as E61 surface. Okay? And from this surface, you can rid off symmetry. How do you rid off symmetry? Well, so this is what we have. we have a time t here, okay? We also have actually a parameter space here. So my parameters are alpha, beta, or kappa naught, theta, infinity, or whatever. So here you have this surface X that we created, okay? And in the surface X, you have this configuration of -2 curves, and you have peak of X. So you get the surface X as a blow-up at 8 points of P1 cross P1. Here you have your peak. Okay, and in this peak, you have anti-canonical divisor class, and there is a special condition that this is a unique anti-canonical divisor class of canonical type that I don't want to explain, but I'll just say that this is a generalized Halpern surface, and that amounts to what I just said, unique anti-canonical divisor, anti-canonical class of canonical type. You can look at the orthogonal complement here, and this is a sublattice, and this sublattice has this sublattice of span of alpha i's, or delta i's. So this were my delta i's over here, and there's another sublattice span of alpha j, and this is my surface. Okay? So this is the configuration of points that we had to blow up, resulting in the configuration of curves. Alpha i's here, this is my symmetry. Okay? And what is symmetry? Why do I call it symmetry? First of all, what are alphas? Alphas are generated by the condition that alpha j dot delta I is equal to 0. So these are vectors that are perpendicular to the delta vectors in the Picard lattice. You can compute what these alphas are, and they are HF plus HG minus E5 minus E6 minus E7 minus E8. Alpha 1 is HF minus E3 minus E4. Alpha 2 is HG minus E1 minus E2. Okay? They also form a Dynkin diagram. This time, this is a Dynkin diagram of type A21. And this is your symmetry group. So you get the symmetry group by just doing very elementary geometry. And this symmetry group, the reason I call it symmetry is, first of all, it's an abstract affine Weil group that has the realization using generators and relations. So you have generators W0, W2 for each of the nodes with the condition that each generator is an involution, and in this case they satisfy the braid relation. That's because all of them are connected. In fact, the braid relation is for connected nodes I and j, and if they're disconnected, then the corresponding generators commute. So that's an abstract group, and you can visualize this abstract group by doing the following picture. Take an equilateral triangle like this, and look at the symmetry group of this equilateral triangle. It is generated by reflections. You can see that my triangle is not very equilateral, but all right. So This is the usual dihedral group D3. Then what you can do is, you can sort of now forget about the triangle and do parallel shift of your vectors. You do parallel shifts of your vectors, or of your lines, and you get a kaleidoscope. You get a regular triangular lattice that is like a kaleidoscope. Then each of these WIs, you can choose like one point, and you can think about this as being W2, W1, W0, I think. So, and then by shifting the mirrors, you create this infinite group. And this infinite group, for example, if you start with this triangle, you flip it over here, you flip it over here, flip, flip, you get a translation. Translation is discrete Painlevé. Right, so each element of this group induces a Backlund transformation, and their particular compositions give you translational dynamics over here, which, when written in coordinates on your surface, gives you discrete Painlevé. Okay, so how do you get these elements? It's probably one thing that I have time to do before we need to stop for the break. It's the following. You have a representation. You have a representation of this A21 on peak of X. Well, if you want it to be a vector space, you can tensor over Z to Q. So, and the way you do it is your WI is a reflection in the root alpha I. Okay? So a reflection here is the usual formula. The class C goes into C minus twice C dot alpha I dot alpha I. But because this is minus 2, this is my root condition, you do this. Okay? In particular, exercise, I don't know if I'm allowed to give exercises since this is not a lecture course but a talk. You can compute that W1 keeps F and sends G to G minus K naught over F. And that's an example of a symmetry of your Painlevé equation. It's a Backlund transformation, but it goes in this direction. You don't fix the surface anymore. You move in the family of surfaces. So you have Painlevé evolution here. You have the symmetry that takes a solution of your Painlevé equation to a solution of a different Painlevé equation for these different values of parameters. And then if you iterate that, you get a discrete Painlevé equation here that you can, by doing a limiting procedure, to get to another Painlevé equation. And we sort of did this full circle. And I still have about half the talk that I was planning to give, but I think it's time to stop and go for a break. I'll stop here. Thank you. Right? Well, if you want, we have 3 translations, but they're all conjugate. It's actually, it's an interesting question, because there is something known as Sakai classification of discrete Painlevé equations, which is sort of classifying all possible geometries. But for each fixed geometry, which is a configuration space, you have infinitely many different dynamics. And then the question is about which dynamics are equivalent, which are not, both on the level of Picard lattice, like are the corresponding directions conjugate or not, and on the level of actual trajectories or orbits on these spaces, but that's a separate story, a little bit more complicated, so maybe some other time, some other day, some other place. Not here, not now. Yeah.
Any further comments or questions?
Yeah.
So you have those singularities, and you remove them, the singularity. How are these singularity points from? From the Hamiltonian structure?
What?
You have that singularity point there.
Mm.
You remove them, and you make the blow up to use this singularity. How are the how do these singularities from?
How do you
how
find
it from? Yeah.
How do you find it?
Yeah.
You do some computation in coordinates. It's basically you write your equation, and for example, if you have f dot, and somewhere here you have something like g over f, you have 0 over 0 singularity. So you basically look at possible.
You use the Hamiltonian formula, or you use
No, it's not in the Hamiltonian form.
And no, one more question is about the transformation. You said the transformation is a discrete pathways. Is this discrete pathway related to that continuous ones?
Yeah.
But just
as I said, if you start with some continuous Paine-Levé and sort of make a circle, this discrete Paine-Levé has a continuous limit to a different continuous Paine-Levé. It's related to that cascade that I was drawing before.
Is the transformation unique? Is the transformation unique?
I'm not sure which transformation you're talking about, but let me say no.
Yeah.
No. I'm sure that whatever transformation you're talking about, no is the correct answer. I think Nikita had a question.
Okay, there's further question. Can I? I need to move out here a bit. Thank you. Yeah.
I don't know where to start. So if I look at Paine-Levé 6, and I think about the phase, so it's a Hamiltonian system. So it's phase space.
Well, it's a non-autonomous Hamiltonian.
It's not an autonomous system, but it has a phase space which has to do with the sphere with 4 punctures, with 4 punctures and representations of SL2, fundamental group in SL2, and so it has it is actually a D4 type.
Yes.
So how does it become in this family? Where this is to E?
So
structure?
So the parameters when you say we have, so you
4
have
parameters.
Right, but you have rank 2 bundle, right?
Yes.
So if you're looking at Paine-Levé 6, you can get it as isomonodromic deformation of a Fuchsian system with 4 singular points. You normalize 4 points to be 0, 1, and infinity. You have 1 point left. This is your time. But then for each point, you have to specify its spectral type. Okay? So you have to specify what kind of eigenvalues you have there.
These are your parameters, alpha, beta, gamma, whatever.
So, right, well, once you specify the spectral type, you can sort of gauge, transform the spectral type so that you have like some thetas living at these points, and these are your parameters. Right. So your Bachmann transformations are like discrete Schlesinger transformations adjusting these spectral parameters. So that's this kind of motion, if that was your question.
My question was, where does the E type, the E structure comes from?
Which E structure?
So you have intersections. I thought the intersections of your 2 cycles. It was an E6. It was an E6.
This yeah. So right. So if you do Paine-Levé 6.
So for generic T.
No, wait. Yeah. So if you do Paine-Levé 6. Nikit, let me show you the picture. I'm in no condition to draw the picture here and without messing it up, but I have the picture here that I can just show you. It may be easier that way. I'm sorry. Unless everyone want to see the picture, I'll draw the picture. No? Okay, sure. What? Yep. No. I don't remember where the picture is.
I have can I ask? I have a question to Anton, maybe Kolya too. So this is
to Kolya.
so which one is so if I have a classical mechanical system, it can be non-linear system. With a quantum mechanical system, acts on functions, a linear thing. But as the space of function gets bigger, then of course this kind of classical quantum linear system contains the classical nonlinear system. Now at this picture, so here Kolya writes Q Knizhnik Zamolodchikov and so forth that are linear equations that have to do.
This kind of things act by linear transformations, but in some arbitrarily large spaces. And Anton writes these things acting by birational transformation on some surfaces. Is there some relation between? Is there some kind of relation between one and the other?
I can answer. Now I can answer. So these are your shift operators. So these translations, these accumulated translations, these are shift operators acting on solutions of the ordinary KZ equation. This is not QKZ, it's before QKZ. Because they change the parameters, these monodromy parameters by some discrete shifts.
But this, in the end, they act non-linearly.
Well, this is a classical limit.
Yes, what I'm trying to say is there's a classical limit in this sort of linear equation that gets.
The quantization of the limit is BPZ or KZ, depending on how you look at it. The monodromy part quantized to KZ, as shown by Professor Rashtikin long time ago. and the way is quantized to BPZ, this was shown by BPZ. And this
Okay.
are
Thank you.
Just this is algeom. This is non-trivial algeom. There are Markov surface, Hirzebruch surface with many similar surfaces. Can you comment on it? Do we have something beyond Penleve, but still with the action of a fine Weyl group? Do we have something?
So in general, if you study various modular spaces of shifts, there's similar kind of Hecke modification. So if you study Hecke modification modular spaces of shifts, then you get a many very high dimensional algebra modular of shifts on surfaces. Then you get Then the Hecke modification modular of shifts on surfaces, they in general some kind of birational transformation that generate this sort of thing. Yes, all of these equations will be beyond Penleve 6.
Well, continuous no, discrete yes. Discrete goes all the way to E8. But I think what happens is if you look at the minimal model like P1 cross P1, if you start adding more points, you lose integrability and you lose affine. So affine is sitting just here.
You can get arbitrary. You can somehow goes arbitrarily high.
Well,
it's just if you want your modular of shifts to be two-dimensional, then you constrain. If you want the modular of shifts to be arbitrary dimensional, then you can get anything you want.
Right. I think Vanya was asking about like the very direct generalization, just staying within that framework, and I think. Yeah, well, okay. This is a fun topic that you can talk about for like a couple semesters. I like it because I think, to me, this whole thing is very similar to algebra geometric solutions of solitons, where you have nonlinear equation and you linearize it on the Jacobian, and then you pull out solutions. And here you have a nonlinear discrete equation that you linearize by translations on PIC and pull it back for birational representation. I think it's very beautiful mathematics. And we're working on applying it constructively to solve various questions. So, yeah.
PIC is kind of infinite. Can you curve it into elliptic curve or something?
Tea break, coffee. As an organizer, I invite everyone for a coffee break and discussions during the coffee break.
Let's thank Anton again.